Deacon. He's going to be talking about dependency ordering in the Linux kernel, and let's get started. Over to you.
Ihan, there's a claim on the chat that the live stream isn't connected.
Well, that's terrible.
I heard that too. I'm going to go and ask the.
Let's hold holding pattern.
I think it's live now.
Okay, is it working? Does anyone know for sure?
Should we start again?
It's live now. Go ahead.
Okay. Take two. I mean, I have to remember what I just said. All right. Well, welcome everyone to the LLVM micro conference. This time virtually for year 2020, as all things. This is probably the biggest and most comprehensive LLVM conference yet, in no small part because of everyone who's here listening to us and basically being a part of this micro conference today. We've got a whole bunch of really great talks on a lot of very important topics to do with LLVM, and I'm personally thrilled at how much adoption and how many people are involved in this particular work now. Starting things off is going to be Will talking about dependency ordering in the Linux kernel, but we're going to be talking about a lot of other things like using Rust for writing drivers and a whole bunch of other things like that as well. But to start things off, I'll turn it over to Will.
Okay, thank you very much, Ben. Let me just start a stopwatch here. Cool. Yeah. So before we get to the great talks that you were talking about, I'm going to talk about dependency ordering and how it's used in the Linux kernel. I'm only going to talk for about 10 minutes. I've got 3 or 4 slides. And then I'd really like some discussion because this is essentially an open problem. And I think the Linux kernel community needs your help, you being the sort of LLVM and GCC community. So by means of introduction, what do I mean by dependency ordering in the Linux kernel? Well, the sorry state of dependency ordering. The way it works really is the hardware level. So if you think of CPU architecture specifically, ARM is the one that I am personally interested in, but there are others. Some people use x86. There's also, RISC-V, PowerPC, and these architectures guarantee, in their documentation, that if you have 2 memory accesses and a dependency, which I'll come on to in a minute, between them, then these accesses are guaranteed to be ordered, externally visibly ordered, so other CPUs will see them in that order. And the reason that this is important is because ordering memory accesses using dependencies as opposed to explicit fences or memory barrier instructions is quite often cheaper, and that's for a number of reasons. One, it might just be that the microarchitecture isn't very good at doing fences, but it might also be that you have a natural dependency in the code that you're writing. You can have a comp exchange loop which has a control dependency on a subsequent store, and maybe you can make that comp exchange relaxed because you know that store is not going to get hoisted up by the CPU. I'll get more onto this terminology in a second, but that's kind of why dependency ordering is important. And so consequently, because it makes things faster, the Linux kernel relies quite heavily on this. It's the basis of RCU on the read side. The way the RCU read side critical sections work is often that you're chasing pointers through linked data structures, and that relies on dependency ordering to make sure you don't stumble across something that perhaps is a candidate for being freed. But it's also used to implement lock-free ring buffers, and even parts of the scheduler. I think Peter's on, so he'll maybe talk about that in the discussion, use dependency ordering to ensure the correctness. And because we're not written in C11, we can't really rely on any aspects of the C11 memory model here. In particular, memory order consume, I think, is widely regarded to be flawed. It's not implementable in a manner that doesn't require fences. The latest version of the standard, I believe, says to use acquire instead. So we don't have C11 atomics, but we do have these things called read once, write once, which you can see here, which these boil down to volatile carts. And I'm going to use read once, write once just in these slides by means of example. So you can think of read once as a load and a write once as a store. That's kind of what we're going at here. So here are the sort of 3 classes of dependency. Please try to use this terminology just because otherwise people talk past each other. I mean, you don't have to like it, but just if everyone uses the same terminology, it's an awful lot easier. So I'll just quickly go through these. The first one on the left is a control dependency. So all of these dependencies are from one memory access to another one, right? That's the first part. So this control one is from this read once. So we load from foo. So we load foo. And then if the value we loaded is greater than 42, we do this store to bar. So between this load and this store, there is a control dependency. And generally speaking, if you have a control dependency from a read to a write, like you do in this example, the CPU is going to order that. It's not going to hoist the write above the load. On the other hand, if you have a read to a read control dependency, so if this write once here was a read of bar, and maybe we store it into a local variable y, those reads are likely to be reordered on weekly ordered architectures, not so much x86.
Will, real quick, if you can you go to hit the plus, go upload things, and set the download option for this? Because I like to. I think everyone like to download these slides. I think these are great examples. I know you can download them later.
I have actually attached them to the proposal, so you'll be able to find them there.
Well, you can download them right here.
Okay, how do I do it? Plus, and then
plus upload.
Yeah.
And then you see the current. There should be a little download icon. The first icon has a slash through it. You click on that, and it'll let people download.
Okay,
yep.
How's that?
You just did it. Yep, thank you. And now everyone can download.
Now I can use computers as well as program them.
Thank you.
Okay, so where was I? Control dependencies. Yeah, read to write generally get order. Read to read not so much, particularly on ARM and PowerPC and RISC-V. I think read-to-read control dependencies can be reordered by the hardware. The CPU can go ahead and speculate that branch and then speculatively do the later load before the first one has come back to resolve the branch. Okay, data dependency. You've got a read to a write here. So you load from foo, we get some value, we add 42 to it, so we're doing some computation on the value that we loaded, and then we store that new value to bar. So this is called a data dependency. You're doing arithmetic on something you loaded and storing the computed result to another location. So this is obviously, well, maybe not obviously, but this is only read to write by construction, because you can't have a read as your second argument, because a read doesn't take a data value. It returns data, it doesn't take it as a parameter. And again, that's supported by remote CPU architectures. Fair enough, let's move on. Address dependency. So this is an interesting one. This is kind of the one which I'd say RCU relies on the most. So address dependency, in this example, we load from foo, so we got X, and then we compute a new pointer using the value we loaded. So we've loaded a pointer, and now we're using it like an array. So we're using a base value and offsetting. And then we get bar, and then we dereference bar as a new pointer, right, for this read once. So this is a read-to-read address dependency. That is ordered by any architecture that has any sense. It's not ordered by alpha, but we put a fence in, so let's not mention alpha for the rest of this talk, please. You can also have read-to-write address dependency. So this second access here could be a write to bar, and we could write, I don't know, 42 or something. The point is that we computed bar from the value that we loaded. Okay, next. So this is where it gets a bit muddy. So the key part of what I just said, other than the terminology, and thank you for putting the slides up for being able to download them, but the key part is that if you have an address dependency, a read-to-read address dependency, like this thing on the left, that is ordered by the hardware. Linux relies on this being ordered by the hardware. We use this in RCU, we use this in other places. However, you could convert that code, and I don't know why a compiler would do this, and this is a kind of contrived example for the purposes of putting it on a slide. But if you converted this code so that we read foo to X, and the compiler says, hey, if X is equal to Baz, let's just use Baz as the base pointer. Now, in this case, assuming for a second that the compilation of this C program on the right is kind of direct to assembly instructions, then the CPU can speculate this branch, figure out it's using Baz, and this is before this load has come back, so it doesn't actually know architecturally what the value of X is. It's just speculated this branch. It's go, oh, okay, I've got Baz hanging around. It's a global variable. So now I know the value of bar on this speculative path. I can do this second read before this first one has come back, and suddenly my ordering is broken, right? So by converting this code on the left to this code on the right, you no longer have the externally visible order that you may require. And that's, that will break code in subtle and complicated ways, depending on the CPU, depending on the compiler, depending on which way the wind is blowing. And that's a bit of a pain. So there's some links here that you can follow afterwards, just to discussions around this kind of thing. And you might think, well, Will, this is stupid code. First of all, why would a compiler do that? But second, nobody has variables called foo and bar in their code. This is ridiculous. Now, this is some code from Linux. And it kind of does the same sort of thing. So this is in the timekeeping code, and it's very important that this read once here is ordered ahead of this load here. Now, this may need to be annotated with read once. It's not, and I wanted to stay true to the code upstream. But for the purposes of this slide, It's this read versus this load here, okay? So we here we load this sequence counter, and depending on whether or not this mask, so it's either, we're looking at the bottom bit of the sequence counter basically, and then using that as an offset off this base to get the timekeeper object. So essentially the timekeeper here, the timekeeper base is an array of 2 entries, and we flip between entry 0 and entry 1, right? Depending on what we loaded here. So here is an address dependency. It's all ordered. It's all good. But if the compiler, and I couldn't convince it to do this, but I'm a bit nervous that it didn't do it. If the compiler converted this to be a conditional, and we actually look at the bottom bit of the sequence and maybe compute the pointer like this, now suddenly you've got a control dependency because you can speculate through this. And now we don't have order anymore, and this will break the timekeeping code. Again, in subtle, hard to reproduce ways, depending on the CPU, depending on the compiler. So that's bad. So normally when the compiler breaks, well, I should rephrase that. When the kernel breaks due to compiler optimizations, and I mean the wording of this quote is unfortunate, and I think the use of the word wrong in here I'm not necessarily going to defend, but it's a quote, so I can't modify it. But normally when this kind of stuff happens, we turn off the compiler optimization, which is causing us issues, right? But in this case, there are plenty of optimizations that could cause the kind of stuff that I've shown. In particular, something like LTO, I fear, could cause more of these optimizations to occur because you might be able to make inferences about the values of pointers based on whole program analysis. And LTO is something I don't really want to turn off because there's lots of benefits. In particular, it's enable CFI, which is performance and security uplift. But generally, we turn them off. So I'd like to open up to discussion about whether or not we can do better than just turning things off. So some kind of questions to get us going. Use these as a guideline. You don't have to talk about this, but I think I've set the scene reasonably. Is we're talking here about dependencies at the source level. We've got a high-level language, C, and we're trying to write code based on a hardware memory model at the CPU level, and we need the compiler not to butcher the dependencies in the middle, and we rely on good luck for that. So is there a way we can enforce these at the source level? If a dependency is broken because of a valuable optimization, can we report that, detect it, maybe even insert fences in those cases if it's worth it? How willing are the kernel community to accept annotations? I mean, we've already annotated to some extent accesses with read once, write once. Could we do more? If you're annotating dependency chains across functions, that's probably not going to fly. Does LTO make it worse, as I theorized? Where do we draw the line between optimizing compiler and portable assembler? I mean, this is slightly there to wind people up, but we are kind of treating the C compiler as a portable assembler here. Yet we want to invoke that portable assembler at O2 because we want it to be fast as well. So it's kind of a difficult trade-off there. And finally, I just ask that please don't throw the C standard at us. We know we're outside the scope of the C standard. There is work ongoing at that link there you can see to kind of get parts of the Linux kernel memory model incorporated into the standard, or the standard adjusted so that we can use it. But that's an ongoing project. Paul is heavily involved with that. It's not going to happen overnight. In the meantime, can we improve the tooling? But kind of that's where I wanted to set the scene. You got just under 20 minutes to fight. Who wants to go first?
One thing I'd like to emphasize with what Will just said, and that is that having an actual implementation could be quite helpful in the context of the standards committee. Because right now it's kind of like, well, what's your implementation? And we have different people kind of doing different things in different places.
Yeah, agreed on that. And also the standards committee are very, as far as my experience has been, they're very driven by existing practice. So if you can show that, hey, this compiler implements these things which are being used successfully by Linux and make some kind of case for that, then that paves the road to standardization. I agree.
I feel like we could really use a large hadron collider here. We need to detect whether or not these theoretical particles exist or not, kind of thing. Trying to detect like where these are in the code. Even like the ticker case in example that you showed, I I get nervous of, do we even compile that right in the first place? Do optimizations tear that apart, kind of thing? And like you said, it's very tricky, to try to throw this in Godbolt and get the compiler to do certain transformations. But once functions get inlined and then additional optimizations are run, is this preserved all the way through? It can be almost impossible to really verify this, right? And I think the thing that's even more tricky without having a way of kind of detecting or verifying this is, even if someone sits down and verifies a binary by looking at the disassembly, you've kind of verified that maybe one version of one compiler happened to get it right. And, I don't know, maybe the next version might do something different, right? It's very tricky.
Yeah, I mean, having a post build step for the Linux kernel, if you build a Linux kernel and then towards the end, a bit like the way Obststrel does things, having a post build step that at least detects that these have been preserved or broken, I think would be a step in the right direction, because then at least we'd know what the state of things at the moment, because we don't really have a good idea at the moment how much of this stuff's getting quietly broken. And if it turned around and said, actually, normally that warning never triggers, and maybe for some people it does occasionally, we might be able to do something about it. But then I think what we would do would vary significantly if it turned out that every other build of the kernel spat out 10,000 of these, right? In which case we probably need to reevaluate our approach to this. Marco?
So I think I mentioned this on the mailing list thread as well, that if it was possible to create a warning that essentially analyzes a build and essentially looks for all dependent load to control dependency transformations, I guess headed by a volatile, having some kind of warning like this. And I had a discussion as well with some people, and I got a comment that isn't this basically implementing memory order consume? And I don't think it is. I think it is simpler, because for implementing memory order consume, we'd have to track the dependencies all the way through every single compiler optimization by pass, and whereas the warning would just have to essentially look at what's before all transformations, essentially take note of all the dependent loads that we want to preserve, and then analyze after all transformations are run. So I was actually looking at this, but I didn't get very far, and it might actually be a bit more complicated than I imagined, but maybe somebody has an idea who has looked at, I guess, dependency analysis and compiler passes before.
One approach that was done by a Google Summer of Code student a couple years ago was to take GCC rather than LLVM and replicate volatile. So make a duplicate of volatile, and weaken the pieces that weren't needed from volatile, but you also need to strengthen other things. So for example, if you load from volatile the temporary, if compiler creates a temporary and loads from volatile, that doesn't have to be volatile. But if you wanted to mark a pointer carrying a dependency, the marking would have to also apply to the temporaries the compiler created whenever it created them at any point, LTO all the way up to the syntactic level. But that's one approach that's at least got prototyped partially. Another one was to, this is some guys on the committee, created a separate bit for each pointer that was marked. And they used the bit to actually carry the hardware dependency. So that no matter what the compiler did to the pointer, you flip you ANDed or ORed or whatever it was the dependency bit back in to preserve it. Of course, that doubled the size of the pointer, so it was unpopular in many places, including with me, actually. So those are two approaches I've come across.
Both of those. Go on, Peter, sorry.
As to annotation, I would love to be able to annotate, for example, say the control dependency, because they are really, really tricky. And there's not really all that many of them, although more every release. But then we'd need something that works for both compilers, and something that they can do something useful with. One in the comments, Alexander says acquire and release are somewhat easier. Yeah, but they're implemented with fences most of the time. And this is really about avoiding the need for fences.
Yeah, I think another thing here is that, like, although it would be great if we could annotate things and then have the compiler honor those dependencies and somehow, you know, avoid optimizations which break them. But I appreciate that that's a huge step, particularly given that the compiler's already written and the optimization passes exist already. But having, you know, to what Marco was referring to, even just having a thing that detects when it's broken will put us in a better situation from where we are now. And that might be a way on the path to actually doing something more clever.
So what would a marking for control dependency look like? Peter, what could we do? I mean, one thing would be to like use a label sort of a thing where you label the load and then you apply the same label to the subsequent store that you want to be control dependent, or I can sort of imagine something like that working. But do you have something in mind?
I do not. And I was hoping for input from the compiler people here, because they know better how the compilers work than I do. And I use them in situations where there is not necessarily one store at the end. For example, in logs or in SMP const load acquire, we spin wait for a state, and it is the exit of the loop that is the control dependency. So the fact that you make progress is your branch, and then every other store after that is ordered versus what happened before your wait loop.
So we want some way to somehow tag a conditional branch that appears in the assembly, but tag it at the source code level. I mean,
Yeah,
maybe by tagging the curly brace or something. Go ahead.
Yeah, make sure that the branch stays.
So
Yeah, and we rely on that quite heavily in locking code as well, I think. And I think I've written some code that uses, I mentioned it earlier on, where you have a relaxed comp exchange and you're just looping around doing that. And there's some stores after that loop, and those stores better happen after that loop.
Yeah, and the control dependency fully relies on not speculating writes, because speculative writes are an immediate out of thin air. So all CPUs will guarantee this behavior. A branch will not speculate stores ever. Otherwise,
okay,
the CPU is useless.
So a question for Peter and Will then. Suppose we had some magic syntax that tagged the closed curly brace. So if you had an if, you know, with a single thing or while with a single thing, you'd have to put the braces in to give it. And then you do something on the closed curly brace to say that this thing is important. Would that suffice for all of the examples you know of or can think of reasonably?
The case I think I'd be uneasy about is when you've got a loop with multiple exit conditions and maybe you only need a control dependency off one of them. But again, I'm not the right person to come up with syntax. I can tell you if it'll work, but proposing.
Okay, so but that is an answer. Another one would be you'd want to be able to tag the break statements and the closed curly brace separately. And that would mean that for example, to make that work, if you wanted for example, you had a while loop and you wanted only 2 of the breaks, there are 5 breaks, and you want 2 of the breaks to have a control dependency, you want nothing else to have that, you'd have to be able to tag the breaks separately. And if you wanted, presumably if you tag the closed curly brace, that means any exit from the loop. I can't see that it making any sense any other way. And so in that case, you'd want to have an endless for loop or something, or a do while one loop, and then have a break for the main, what would have been the main condition. So you could just say the normal exit from the loop only, but none of the error exits. And then you have a question of what happens if you return out of the loop. And you could imagine having a control dependency extending from one loop body to the next, which would mean you'd want continue, and that might also apply to the loop. I mean, so we don't normally have loop control dependencies. Other people sometimes do.
I think one of the things that I'm most interested in is trying to figure out which transforms in a compiler are maybe destructive or kind of lossy or kind of problematic transforms, and trying to figure out what's a reasonable way to try to disable these, right? Is I'm always curious about, for like certain functions like this where we're kind of curious about the behavior across multiple compilers and versions of things. Is it realistic for us to disable some optimizations there? I'm guessing a lot of this RCU code is hyper optimized to the point where you probably don't want to be compiling individual functions at 0. But I think at least in the case of LTO, I think if there's concerns around like, well, if this function gets inlined and then maybe in the caller now we have more information about some of the parameters, I'd be interested in even marking some functions that have external linkage as no inline, and then verifying that via LTO. We don't deduce any information about the caller kind of thing. But I think another thing that's a little tricky, at least within LLVM, is as soon as you have visibility into a definition of a function, the compiler can start to perform analyses to deduce more information than was provided by the language itself. So it can actually figure out a parameter was non-null, for instance. And I'd be curious about, maybe it would be helpful to have some kind of function level attribute to say, like, don't perform that kind of analysis on this function. Like, treat it as a black box, as if it was from a separate translation unit. Really don't try to do anything more clever here than you would as if it was separate translation unit.
I suppose, like, what's a way forward then? Because certainly from the kernel side, I would be willing to test out ideas, give you feedback on different proposals, and continue this discussion. I think Paul and Peter almost certainly would as well, because we know. Honestly, it feels like we're on borrowed time here. There will at some point, something's going to go horribly wrong, and nice to have an answer for it, other than use yesterday's compiler instead of today's compiler.
I'm certainly more than interested.
Yeah, so a few days ago at the bin utils BOV, I suggested having a Linux toolchains mailing list where us kernel people can contact toolchain people. This has since been proposed to Postmaster, although I've not seen Dave reply to it yet. But such a list would be great to hash out these things as well.
Yeah, as long as it's not just all kernel people, but if you say it came up in the bin utils BOF, I suspect then there's other people involved as well, which would be good.
Yeah, the idea was to have both toolchains, Llvm and GNU people on that list.
Okay, cool. How much longer have we got? Keep an eye on the time.
You have 6 minutes.
6 minutes. All right. Maybe we can go through some of the stuff in the chat. Would that be useful? But please interrupt me if anyone wants to say anything. Nick.
Sorry, I was just getting the 5-minute warning card ready.
We now have what? I've wasted a minute looking at the chat. Right. So what do we? Is there anything in here that we need to talk about?
When you guys mentioned this, I kind of jokingly said this, but actually it's kind of serious about if you were to use the tag volatile for some of these conditionals. If you're volatile is basically what that means, right? That you have some sort of dependency on this being where it expects. So if you were to have, like, at the end of the, like Paul mentioned, a squiggly bracket, volatile or volatile break or volatile go to, that's a way of telling the compiler that you wrote your own. Come on, use the official one.
I'm a peasant. I don't have a printer.
So, is that actually just okay? That's a joke.
So one thing you could do right now, okay? For example, the example we have right here, if you declare TKR to be volatile, you would take care of some things but not others, right? Because if TKR is volatile, then it has to store it and then it has to load it again, and it can't split out it is not allowed to split the the assignment like it did in the right-hand column. Now, I'm not saying that that is sufficient for control dependencies because there's all sorts of, because the compiler can do all sorts of things rearranging volatiles with non-volatiles, but it would prevent this particular optimization. Okay. However, that gets back to if you do that, you could declare all your variables volatile, and that would get you pretty close to a portable assembler. Because it would disable pretty much all optimizations. Yeah. So it's probably not what we want to be doing, but it might be worth a try. My concern, though, is you're going to be adding a bunch of extra, the CPU is plenty fine pulling variables up into registers, and control dependencies work just fine with that, okay? But volatile is going to say, no, you're not doing that. You're storing it onto the stack unnecessarily and loading it again. And that load hit store is a killer on many modern architectures, or at least it was a few years ago. But yeah, using the volatile keyword, for one thing, that'll annoy JF Bastion, so that's worth something, I think. I don't know.
Well, obviously, if we were to actually have a volatile keyword or something that was used, it would actually be wrapped in a macro saying, control dependency or something like that. Because obviously, it'd have to work on older compilers that don't allow that, and you have to have some sort of detection that says this doesn't work. Just make it a empty. Like we do
Peter in the comments suggests putting volatile before the loop constructs. So volatile if, volatile while, volatile do, I guess. Why not? And then you'd have volatile break and volatile continue, I suppose, to cover both cases. Sorry, Will, I talked over you.
No, I talked over you. Marco's also suggested volatile code blocks, and it would disable all optimizations, and in some cases that might be okay. Very small. Compute this pointer type things.
That could be good. Although in the cases you were talking about, you just wanted to preserve the branch corresponding to a given break or continue. Mm-hmm. And so having volatile on a code block makes a lot of sense to me. And in this case, it might work just fine. Put this thing in a curly brace volatile, and maybe that's enough. Okay. Mm-hmm. But as Nick DeSolnier said, who knows what else the compiler can do, right?
I mean, I'm terrified that we get any of this right at all. It makes me very nervous. So I think one action item that I'll take is the LLVM developer conference is coming up. It's going to be virtual kind of thing. And I plan on talking to both. I'm going to try to get a hold of JF, and also I think Eli Friedman, it looks like to me, wrote a lot of the initial documentation on how LLVM models memory ordering. And I plan to try to sit down and talk to both of them, at least in try to get their feedback on the problem, and how might we provide useful tools to people that would be able to leverage these things.
My concern with all these suggestions about putting volatile in various places is that it still requires people to basically find these kinds of things. I think we need better automated tools to actually point out where these problems potentially are, because I don't think it's going to be obvious to most people. And not all code is as reviewed as others, as we all know.
Would you need something like a static analyzer to look at the code and then find all the places that have a volatile, and then then you have to have something that could read the assembly.
It's worse than that. You'd have to
assuming that they're in the right place. Sorry.
You'd have to, if I throw the Steve standard myself, you'd have to pollute all the internal representations in the compiler with extra volatile thingies attached to new stuff. Which may be what has to happen. I can't see how you solve the problem completely without that long term, but it's not an easy step, at least not from talks before.
I beat you.
This is such an important topic. Thank you very much, Will.
All right, thanks everyone. Cheers. Well, I'll see you on the video.
Okay, next up, Jeffrey's going to be talking about Rust.
Great.
Here, let me give you presenter, and there you go. You should be able to flip the slides around.
All right, cool. Let's see how this works. All right, thanks, folks. This is a session that's been worked on by a handful of us, and so I'm going to sort of go through a couple of slides very quickly, and then I just really want to get to discussion about what we need to do, sort of what the steps are, what the right way to make this happen. And so I think people have seen a couple of mailing list discussions. Alex and I have been working on a project to make bindings for module code. John has also been working on the demo. Half of us have been trying things. And so how do I move slides forward? Okay. Right. So what is Rust? Why should we do this? Why are we interested in having Rust in the kernel? It's well suited to the kind of development that we do in the kernel. If you look at what things that Rust improves over C, it's very similar to the way in which the kernel is already trying to take C. In that it's a compiled language. It doesn't have garbage collection. It doesn't have exception handling. You return your error types. You pass them very manually. It doesn't have C++ style OO. The OO it has is very similar to the kernel's obstructs. Doesn't sort of call functions that allocate or do things behind the scenes without being explicit about it. Very strong emphasis on zero-cost abstractions. Stack model and so forth is similar to how C works. It has a concept of safe and unsafe code, where you can say, most of my code, I'm not doing funky things with pointers, I'm not having multiple access at the same time, and so forth, which means that your unsafe blocks are much smaller, easier to review. So you make sure that anything you're doing tricky, and I'm kind of glad to be put right after Will's talk, because I feel like part of this is we want our compiler to know more about what the code we're doing is actually trying to do, so it has a little more intelligence about it. And so nowhere in Rust code, in safe Rust code, is a concept of undefined behavior, and I think that's a thing the kernel community has been mad about for a while. Is sort of, why is the compiler calling this perfectly reasonable thing I want to do undefined? And then turns out that's because C does not give you enough information to track. What are you doing with this? And so I don't want to go into and then of course there's the yeah, we're just done with that. I don't want to go into too much detail about what the Rust language is. Alex and I gave a talk at Linux Security Summit last year. That's going to be linked in the slides. Can I press is the download enabled for this? Can folks get to it?
Only the presenter can enable it. If you hit the plus in actions and then say upload, and then upload. There's the first icon, has a red slash through it. Okay. Yep, looks good.
Yeah. So in a couple of slides, there's a link to our talk from last year. So if you want to see sort of an intro to the Rust language, I don't want to go too much into that in this session to make sure we have time for discussion. The other big thing in the room is 2/3 of security bugs in the kernel, in other people's kernels, in Android kernels, distro kernels, just a remarkably consistent number is memory safety bugs. And so Rust tries to avoid use after free bugs, buffer overflows, double freeze, those sorts of things. I'm not saying they're all going to be magically solved by using a different language. I'm saying, this is in scope. This is a problem that people have seen since C was designed a very long time ago. We should have language level tools to address. So what we're not suggesting here, just to get this out of the way, is let's take 25 million lines of kernel code, turn it all into Rust right now. Where we're proposing we add the option of using Rust for new code for whatever that looks like. Maybe it's just drivers, maybe it's core code, but no one's going to be rewriting an entire kernel overnight. So just to set the stage, here's an example of some code that Alex wrote. It's a device node that acts like the get random system call, which is to say it blocks at startup, but once the random pool is initialized, it doesn't block, so it calls the kernel get random function. You can see the full code on that GitHub site. This is abbreviated. This is just the read function, but you can see a couple of things. Number one, it's all safe code. Nothing in here is doing manual bounds checks or manual sort of. Every pointer dereference in this code is known to be safe. And there's a couple of other things I wanted to call out here. The error handling, there's a little question mark syntax, which is not exception handling. It is local control flow. It means, pass this error. It returns an error code, just like the kernel does already, but no risk of getting, the go-tos wrong and so forth. The slice length is handled for you. You cannot sort of, all of these things where they pass around, sections of arrays, you pass them around as a single unit. You don't have to worry about, do I have to pass this len or do I have to pass the other len variable or whatever. It sort of goes with the variables, and that all of your slices are valid. And this sort of intuitively, I think I want to say is, number one, the syntax should probably be familiar enough to you as a C person, and number two, what it's compiling into is should fairly obvious. It's not doing anything super magical behind the scenes. It's just, it's just doing more checks and carrying more information and types. And so, how do we get there? We should integrate with Kbuild in some fashion. We may or may not want to use Cargo. That's the thing I want to sort of discuss. Cargo is Rust's build tool for managing dependencies and building things, a little bit higher level than the Rust C, raw compiler tool. It does have the ability to download dependencies from the network, in the way that pip or gem or npm or whatever would. We don't want to use it for that, of course. We're only going to make entry code work. Of course, kernel build should not require grabbing dependencies from the network. Cargo very much supports grabbing dependencies from vendor dependencies that are in tree, and that's been done before in the kernel code. There's plenty of precedent for saying we're taking some code that someone else has written that's under compatible license and putting in the kernel tree, and now it's just a normal part of the kernel tree that other people can edit. And so that's I think that plan makes sense, but open to always discussing this. And so I know there's been a lot of questions. I want to very quickly open this floor up for discussion. I've got some more slides if people have specific things that they want to talk about, but I just wanted to say, what should we do? How should we do it? What? Yeah. So open floor for discussion. And I'm also watching the chat a little bit.
Yeah, Josh, I think it is definitely true that the kernel would be able to use the compiler's core and alloc crates. We definitely use those in the sort of out of any tree module that Jeff and I have prototyped.
Yeah, just for a brief overview for people who aren't familiar with the division of crates within Rust, the standard library is kind of broken up into three major tiers. There's core, which should work just about everywhere. There's alloc that works anywhere you have a memory allocator, which obviously includes the kernel. And then there's standard, which is higher level OS functions that assume you have things like read and write or a file system or similar. So the expectation would be core and alloc should work fine in the kernel, and standard would not necessarily be expected to. We might selectively grab a couple of pieces if they're really important, but for the most part, core and alloc would make up the functionality people would use for in-kernel Rust.
Right, so looking at some questions in chat. How would this work when interacting with existing data structures, such as PCI objects, function callback structure, RCO lists, etc.? Rust has a pretty robust concept of binding to some existing data functions, etc., and declaring in Rust what the ownership guarantees are of this code, and saying, okay, this code is passing a pointer and taking it by ownership, or returning something that you need to own. I will take these raw pointers and encapsulate them in the right types. So I can put some links up, but we have, if I go back a couple of slides to this read function, this read function is implemented on a Rust trait. If you notice the ampersand self, this is a trait that matches the file operations structure for a character device. And so what we're actually doing in this module is we generate a extern C callback function, which is specific, which is templatized onto this trait. And so it polyinstantiates that, and that gets us the obstruct, the sort of C-style obstruct. And it says, okay, you've got a shared reference to your file object. You can work with that in various tools that handle non-unique references, like you can take a lock if you want to modify something, etc. For RCU, I just got some bindings written up last week for that, at least for the read side. You make a local variable, which is a read side barrier. And you say, as long as you hold this, you are inside a read side critical section, and then you can pass that off to functions that expect to dereference things, and therefore the compiler is checking for you that you are in fact in a read side critical section. So there's a way to do that. I can give some examples of that if you've got questions.
One question I have related to some of the bindings is, and we've discussed a little bit in the past, is like the use of in leveraging bindgen to help kind of keep track of kernel interfaces, at least when they change, is something on the Android side that we're kind of focused on trying to study right now around details around ABI changes and stuff. And I guess I was curious, because when you mentioned about kind of signatures and lifetime and ownership, can people use bindgen but then like manually go in and change the generated bindings to provide more information about lifetime? And
Yeah,
No,
so
the usual way bindgen is used, in my experience, is bindgen gives you like a very raw binding, like raw pointers, no lifetime knowledge, and then generally you develop a safe Rust API on top of that encapsulates what you think the lifetimes are that map to that C, because raw C does not have lifetime markings in any way.
right. So by bindgen, everything bindgen generates is tagged unsafe. You almost always want to write a small Rust wrapper on top of it that checks what the guarantees are, which might be just, this is a non-null pointer, this is a well-formed Rust pointer or something, passes it on, and it's okay. But it might be more subtle than that. For instance, the for each process iterator, which I just linked in the chat, since for each process does RCU dereference, you need to be in an RCU critical section. And so the safe way to call for each process is you pass in this guard object that says, yes, I am in a critical section, RCU read critical section in order to do it. And so you use bindgen sort of just to match your ABI, to match whatever the C compiler is doing. So you're not reading all of these C definitions by hand. You write your higher level bindings on top. And yeah, I think a core part of this is we need to write good Rust bindings that encapsulate all of the hidden knowledge of, oh, when you call this, you need this lock and you need that context. You can't do it from the interrupt, that sort of thing. All of that should be you should be able to write code. And it was quite great when I forgot to pass this guard object. It was like, you're missing this parameter. A couple of questions I want to address about alloc, unless folks had more questions about bindgen.
One follow-up on bindgen as well is that this is an area where we can absolutely enhance it more in the future. That I think in general, if we want this to be maintainable, we do not want to hand write bindings to any more than a tiny tip of the iceberg of kernel APIs. We want as much of that as possible to be automatically generated from kernel APIs. If we need to perhaps add a little bit of hint in the C code that bindgen can pick up on, then perhaps we can do that. But we don't want to be in the position of, oh, well, we want to use this new area of the kernel, so let's spend a bunch of time adding Rust bindings to that part of the kernel, and then somebody has to maintain them. That is not the goal. I think we want to have some cases where that's unavoidable. There will be some cases where we need to write a higher level Rust binding to something very complex in the kernel. But in general, the more we can automatically generate so that any new API written in the kernel can automatically be used from C and Rust both, the better. Automation is a very good thing.
Yeah, I'm interested. I haven't been following this very closely, but I know there's been some work from Google on auto-generating safe C++ bindings using the natural shape of C++ as hints to say, okay, you're passing an STD string. We know that that's well-formed, etc. I don't know what it would look like, but it's in what the kernel code that is. But certainly, it sounds like there's precedent for you put enough information in the thing you're binding to that you can write an automated bind generator that gives you safe bindings. Architecture support. I know some folks were asking about that. I'm gonna switch to that. There, just sort of very quickly. Yes, there is one complete implementation of Rust right now, which is Rust C, which uses Llvm as a backend, which is a limiting factor for, oh, I want to replace, drivers, char, TTY, whatever. If you're trying to say, I want to take something very core that everyone uses, I don't know how much of a restriction this is if you're taking something that is architecture specific. I don't know if we want to entertain the option of saying, we're going to use Rust in architecture-specific ways. So that's open question. I'm curious what people think there. Rust is all of these architectures are fine on Rust. Arc and Spark 32 have Llvm backends, do not have Rust ports. A handful of the remaining architectures have some previous attempts at LLVM ports, but not very much. And so yeah, alpha is one of the, is it going to exist there? There are some other options. As we mentioned, mrustc is a Rust to C compiler that assumes that you have already checked the code is valid with the official Rust C compiler. So it does fewer of the checks, but it will generate C code, and then you can compile it with your favorite C compiler. There's a couple of other efforts. Julia team is working on an Llvm C backend because Julia also depends on LVM. People want that in more places, and so there's a couple of efforts at getting a GCC Rust front end, et cetera. So, how is this a hard barrier? I don't know.
So regarding the architecture support in Rust, I'm actually working on the RFC in Rust for what tier each architecture is and how we promote more architectures and get more architecture inclusion. We're working with several folks who care deeply about less common architectures. And I can tell you that when Rust got into Debian, for example, that was already a point where all of the hobbyist architectures and more obscure architectures came out of the woodwork to start making sure that that support is reliable in upstream Rust. So I wouldn't worry too much about that one. Effectively, there is the limitation of if you don't have LLVM, then you won't have Rust. And that's likely to stick around for the foreseeable future. But that's already been an issue for those architectures to begin with. If you don't have LLVM, there's a lot of fun things that you don't have. And in the meantime, any architecture that does have LLVM and people care about running Rust on it will get Rust running on it. I don't anticipate there being any key problem there. Beyond that, yeah, we're not rewriting the core kernel in Rust tomorrow, so this may start out more of a, there are some new drivers that exist for, say, PCI Express devices. Like, if you write a PCI Express driver in Rust, it's not going to matter if it doesn't work on an architecture that only ever had ISA or only ever had some pre-PCI bus. It wouldn't have worked in the first place.
Yeah, I think one of the things that I wrestle with a little bit is, we have some ideas for drivers where we're really interested in enhanced kind of memory safety, and some kind of argument that we shouldn't even try to experiment to do this until LLVM has a PA risk backend, to me is, I don't know, it's kind of curious.
Yeah, so that's, are people comfortable with landing Rust support in the mainline kernel, knowing that there is no, cross, which is a thing that, I think both Linus and Greg had specifically said of, I want Rust to be on by default, at least if you have a Rust compiler installed. Is it enough to say, if you're on one of these arches, x86, PowerPC, ARM64, several of them actually, there might be some arch-specific code, or it might be, specific driver. Well, I don't know. Verdi is probably not a great example. So something that's a little bit arch-specific, where we say, this driver does use Rust, but we know that Rust exists on this arch. It's dependent on the arch. It's config whatever arch specific. Is that fine? David, yes, I'm happy to encourage it. It seems like the question is how about more encouragement for a Rust front end for GCC? I think that would be awesome. I don't know how to make that happen. It seems like a sizable project, and I don't know who are the right people to work on it. There are two, linked in this issue here, if you go there, there are two efforts in progress. I don't know at what point we want to count on those being stable enough for use in the kernel.
Right. There is actually a work in progress. There's some work in progress code to have GCC take Rust's intermediate representation and compile that. And some interesting project and an interesting approach, taking Rust's mir and compiling that through GCC to an arbitrary architecture. It's a really interesting potential approach for adding more obscure architecture support that perhaps LLVM isn't wanting to maintain upstream. But I think this is the kind of problem where if the notion is let's block getting into the kernel based on architecture support, then we will never get in. I would personally propose the reverse of let's get into the kernel, let's work on the majority of architectures, let's use it in cases where people will not deeply miss the absence of a handful of drivers, and then this will start to drive the interest from people who care about those architectures to make sure that Rust works on their architecture.
And I think there's a bug bounty. It sounds like people were just talking about yesterday that's starting about a GCC front end for Rust. So I think if people are interested, maybe they can help fund that project.
Yeah, there's also one of the issues we haven't really discussed is ABI, and Rust is backed by LVM, and does, for ABI reasons, that mean Rust kernel modules are practically only loadable from a Clang built compiler? And if that is true, and I think several of us have discussed that truly understanding the ABI implications are beyond any mere mortal. But if that is true, that Rust modules are only loadable from a Clang built compiler, then you are already in a position where you're bound by the set of architectures of Linux on Clang builds. You're no worse off, in other words.
Yeah, so this one's subtle. I feel like I've tried to explain this in private conversations, done a very bad job of it. So I'm going to try again and sort of see if I can do a better job. There is a front end and a back end compatibility component here. The back end component is that rustc, the official, assuming for the sake of argument that we don't get a working GCC Rust compiler anytime soon, the back end is LVM, and so you could match the liblvm version that you're using to compile your LVM built kernel. The front end is that bindgen uses libclang to parse your C headers. So if you've got a sizable amount of C headers and you want to presumably interpret structs in the same way, interpret if-steps in the same way, interpret all sorts of other things the same way, you want to be using, ideally, the same version of libclang, interpret function calling conventions, all of that. You want to be using the same version of libclang. If you are worried that cross-compiler version dependencies is a thing that is likely to break, which I think is the kernel's consensus position, that we don't want to rely on the fact that even though the ABIs are pretty well specified, we don't really support, okay, I'm going to build my kernel with GCC and my modules with LVM or whatever. Do we want to support that? Because we would imply supporting that. If we don't support that, are we going to be restricted to Clang-built kernels? If we restrict ourselves to Clang-built kernels, is that okay?
It's also worth noting that even if this were compatible, even if there's no particular issue doing GCC together with Rust, which in general there never is, because this is what people do in user space all the time. GCC is the common C compiler, and people link C and Rust together all the time. But nonetheless, the other reason why you would probably want to favor a Clang compiled kernel if you're using Rust is that Rust has full support for cross-language optimization. That if you compile with Clang and with Rust using the same backend of LLVM, you can optimize across language, which means that you don't have to recreate things like inline functions or similar. You can write an inline function in C and call it from Rust, for example, or vice versa. And inlining will work, specialization will work, any kind of optimizations will work without having to say, well, we'd better write an extra bit of optimized code in Rust so that we don't lose an optimization compared to if we'd written it in C. So we may want it in order to reduce friction at the boundary.
So I think if I understand Greg KH's argument, I think he's on the call, so he can correct me if I'm misrepresenting his point. But I think one of the things is it's insanely complicated how many things go into a ABI, and so you can only really have strong guarantees about ABI compatibility if you're using the same exact version of the compiler when compiling all of your objects. In particular, if your toolchain is configurable, let's say, and someone says, I want stack protector on by default, implicitly if unspecified, and they build their kernel, and then later they use DKMS in a different compiler that doesn't, and you link these objects together, you have a different ABI. Is that going to cause a crash or a panic? Some of these ABI differences are unobservable, and maybe you could get away with them. But I agree with Greg that to like you literally can't guarantee anything unless it's the same exact compiler, same exact maybe even front end for LLVM. I don't even think we know necessarily about that.
Yes, everything has to be identical. We don't guarantee otherwise today.
So my question is, should we think about relaxing that guarantee, or should we think about constraining Rust to kernels that are otherwise built with LLVM so that everything is LLVM all the way down? Until such point, yes, until such point as a GCC Rust backend or front end exists. If we say we're constraining ourselves to LLVM, is that okay for mainline?
But why can't you build your kernel side with GCC and you build your Rust side with your LLVM backend, but you know all the options and everything at that moment in time, and you know they all work and they know they all match. You do this today. I mean, as long as that happens at the same exact time, you're fine. It should work. I mean, you're probably testing it today and it works, right?
Yeah, we are testing it today.
Yes.
We're right. Yeah, we have a CI that works great on whatever Travis's default kernel is. So,
okay, so I mean, you're linking against, you're creating from .o files that are created with that, and you're fine. You're good to go. So that's fine. I wouldn't artificially constrain yourself at this point in time unless you find out there are major problems.
Okay.
So to be clear, we use this every day in user space, and it does interoperate. It has to interoperate or people will be extremely unhappy. So the primary reason we were talking about limiting it was not because there is any limitation in Rust, but because we were getting feedback from kernel people that were saying, oh no, mixing compilers is completely unsupported, don't ever do that. So we were saying, okay, we can go along with that. If that's not a requirement being imposed, then it's certainly not a requirement from the Rust side.
Well, we don't, if it breaks, you're on your own, but.
Right, exactly.
Let's give Florian
I
think Florian has a point he's looking to make.
The issue is also whether you are using fancy features like bit fields and stuff like that. The core struct layout and core calling convention will be compatible across compilers. But if you use struct by value return structs with bit fields and whatever, then you get this explosion about in the ABI space where things get uncertain. But I think that's also an area where Rust currently lacks expressiveness. So at the interface, you would sort of stick to the minimal C ABI, what people view as a C compatible ABI, and you would be fine there.
Right. So one thing that I think is definitely a good idea is to say we have tested these particular versions of Rust C/LLVM against these particular versions of GCC. Here is a test suite. Here is a thing you can run, which will generate some. And honestly, BindGen does this. It generates some test case which says, okay, do the sizes and alignments of things once they have passed through the Rust compiler match exactly the sizes and alignments and so forth and offsets that we saw when we were parsing the C, just as a sort of extreme safety check. So we could be doing that. Okay, so since we are short on time, I wanted to mention a couple of follow-up things. We have this channel over on. I guess I got to move very quickly, but I'll finish up. We have a channel on Rocket Chat. We have some times when Alex and I at least will be around for meetings this evening and also tomorrow morning, half an hour beforehand. So we'll be in the chat room in Rocket Chat, and we can jump into a hack room. But I think that getting some agreement on the just to summarize, I think we have some agreement on the question about should we support cross-compiler seems okay. Should we support architecture support seems maybe a little bit contentious, but restricted architectures, but probably fine. Thank you all.
Great. Thanks so much for the presentation, everyone. Certainly a lot more to be discussed around the topic. So great introduction. I appreciate it. Cool. So the next talk, my colleagues Bill and Sammy and I are going to talk about some of the compiler optimizations that we've been deploying in our various distributions, the kernels in our distributions at Google, and kind of brief overview of what they are, but more so kind of discussion about upstreaming and implications on testing and stuff like that. So pretty much we are using LTO PGO and auto FDO now in at least 3 different kernels and 3 different distributions that we have across Google, kind of thing. And I think for us, getting it upstreamed and getting it to work with kind of multiple compilers is something that we're looking for kind of help with. It's something that I don't really want to be carrying out of tree much longer. I would like to try to get these things upstream as soon as possible to kind of reduce downstream maintenance burdens, but also get this working for other people as well. So I think yesterday, Mr. Llvm from Microsoft had a presentation on some of this using profiling data as well. And so, it's kind of interesting that people are working on this in parallel downstream, separate of each other. And I really wish that we would be collaborating and, working through the details and getting something upstream that works for everyone. So I think that's kind of the next steps where we are and really what we'd like help with. Sammy, you want to talk a little bit about LTO?
All right. So what is LTO? As you know, LTO stands for link time optimization. In practice, with Clang, enabling LTO means that the compiler will produce Llvm bitcode for each C translation unit and only compiles it into native code at link time, when it can also perform additional optimizations such as cross-translation unit inlining, for example. This is a relatively simple concept, but it does have a few consequences. First of all, Llvm requires us to use its integrated assembler for all inline assembly with LTO. While the assembler is in a decent shape these days, this has been a constant source of compatibility issues, some of which we are working on fixing still. Second, using LTO means that we won't have native code until after everything has been linked, which means that any processing that assumes that we have an ELF object file after the compiler is done will have to be postponed until after the kernel or the modules have been linked. This requires some changes to the build process, but it's not overall a huge problem. Third, we can't rely on the linker to preserve the link order for init calls. Instead, we have to explicitly define the order using a linker script. And finally, linking the kernel is obviously going to be slower. Llvm originally supported only one method of doing LTO, now known as full LTO, which takes all of the bit code produced earlier, merges it, and analyzes the entire program at once. This unfortunately uses a ton of memory, can't really take advantage of all the CPU cores, and therefore doesn't scale well for larger programs like the kernel. Llvm developers later came up with thin LTO, which appends a summary to the bitcode files, and at link time only looks at the summaries when analyzing the program. This can be done in parallel, and therefore linking is going to be significantly faster with thin LTO. And the more CPU cores you have, the faster it will be. I'll show you some rough numbers in a second. So even though full LTO is far too slow for development use, it's still useful for production builds because it does produce faster code in our experience. Google has shipped LTO kernels on Pixel phones for a couple of years now, but performance is not actually the main reason. We use LTO because it's needed for control flow integrity, which adds a runtime check to each indirect call to limit the number of possible call targets, which makes it harder for an attacker to alter the control flow by modifying function pointers stored in memory. And in order to perform this type of analysis, the compiler needs visibility to the entire kernel, which LTO provides. We maintain LTO patches for the tip of tree kernel, and as many of you are aware, we are still working on upstreaming this code. We currently support ARM64, which we primarily use, and we also have x86 patches because I hear some of the people who use that architecture as well. Okay, let's look at the impact on build times. So these numbers were measured on a fairly powerful workstation. As you can see, with a sufficient number of CPU cores, clean LTO is not much lower than building the kernel without LTO. Full LTO, on the other hand, is around 5 times lower, and especially when building an ARM64 kernel. It also uses dramatically more memory. All right, back to you, Nick.
Thanks. I'm just going to make sure that the slides that folks can download it real quick. Sorry about that. Wish the default was different, but cool. So those should be downloadable. So I think one of the questions that we've had on the mailing list has been, you know, how can this possibly preserve kind of inline assembly kind of thing? And I think one of the things that's interesting is there is the notion of kind of post-link optimization. So there's kind of neat projects right now, you know, kind of still early kind of research-ish stage, but people are starting to deploy these kind of thing. But we're essentially not doing optimizations after we've already linked a binary, while we kind of defer most of the compilation to the link step. We've only kind of run the compiler enough to generate the intermediary representation, and then at link time, we still have the full semantics of the program. So these are two distinct notions, and you know, while we'd like to play with post-link optimization, probably won't be for another, you know, year or two. And right now it's just kind of focused on LTO. So just kind of noting that those things are different. And then from there, so Sammy kind of talked about, you know, how can we analyze more of the program to kind of find or perform additional optimizations. And kind of another like peanut butter and chocolate thing that we think about is if we had information about how does the program operate, could we do better kind of program like code layout, or could we take really hot code, just like if you know how like tiered optimizing JIT compilers work, is, you know, you really want to maybe take the time to heavily optimize really hot code, and then for code that's never executed, you know, maybe just compile it quickly, or don't worry about it being the most optimized thing ever because maybe it doesn't show up in a profile. So, you know, if we can collect profiling data and feed that into the compiler, you know, we actually can get some pretty nice performance wins. And right now, kind of statically, we can annotate the kernel using this compiler built-in expect. In the kernel, we wrap that in a macro, likely and unlikely. I think one of the things that's curious is, can these static annotations go stale over time? And so there was actually a really cool intern project that built this utility called Clang expect, where basically if you do feed profile data into this utility and it kind of wraps Clang a little bit, it can actually verify and tell you when you have built-in expects that are kind of against what the profiling data tells you, which is kind of interesting. We haven't run it yet on the kernel, but I think we should. I think it'll be interesting. And for the profiling, we're going to talk about kind of the two different ways that you can collect it. But I would say more so, it really comes down to your infrastructure in your pipeline. I think, you know, both of these things are a little bit complicated. They complicate the build pipeline a little bit, kind of thing. And it just reminds me of like I've heard the expression used in machine learning is that you know, it's a credit card for technical debt. A little bit is you know, wiring up build systems to collect and feed these things back in is actually probably more work than wiring up the build systems to make use of this, honestly. And another thing that's important as well is really data is super important for this, data integrity. And, you know, measuring what's important is a double-edged sword, right? Is, you know, we worry about, you know, do you get something wrong if you're using training data that you don't actually care about? You know, does that create a release build that is actually problematic in other cases? You know, it's certainly open questions, right? So I'm going to turn the presenter over to Bill, and Bill's going to talk about PGO.
So PGO is program-guided optimizations, which obviously just the same as FDO. Clang offers two types of profiling, or more to the point, two ways of instrumenting your binary. So one of them is the IR instrumentation. In other words, the intermediate representation, or the instrumentation is placed in there during, you know, normal transformations of the code. Otherwise, there is front-end instrumentation, and obviously, as the name implies, it puts it in there at the front end, basically when it's generating the IR. And so the differences between the two, basically, it's that besides which places in the compiler it inserts the instrumentation. The IR instrumentation has a couple of benefits, such as early inlining, for instance, and it has some more. It's more context sensitive, with this information. So basically, the TLDR on all that is just use the IR instrumentation, unless you're trying to go for something like coverage, in which you don't really care much about performance. You just want to know, is this actually executed? So let's see here. Sorry, I have to. Next slide. Okay, so how do you actually do this with Clang? So an example workflow is as I have placed here. There is an experimental new pass manager, which is just an interior change in Clang, and it's best to use that when you're using this PGO, basically. So obviously you instrument the kernel and you supply it with this flag, the profile generate flag. In our implementation, we placed the PGO data into a similar place that the FDO data is, or the Gcub data, actually, basically. So it's in sys kernel debug PGO prof raw, and we'll get to why it's named that in a minute. So similar to how you do the Gcub stuff, you would do a reset of the information. So then you run your load tests on that machine, and then after those are done, you can copy the prof raw data into some file. Now, on Linux, I'm sorry, on Clang, you have to process that raw file. So basically, there is a tool in Clang called Llvm prof data, and the command that you want to run there is the merge command. And actually, as that implies, you can have a whole bunch of prof raw files and smush them together into one prof data file. And so after you've processed that file, you can now use it, obviously. And so you recompile the kernel, and you will get, and you do the profile use, and you pass it the prof data. And this is, of course, kind of where this experimental new pass manager is more important, because it's actually going to give you much better use of your PGO data. If you're going to be using this with LTO, so obviously a lot of this, the transformations are going to happen during link time, of course. So you can pass it this flag, which is LTO CS profile file. And that that will use the profile data to do that. So it's a very simple workflow, and it's going to mirror a lot of what GCC FDO would do. So it shouldn't be too, out of left field for people. So what are some of the benefits that we can get from this? So internally at Google, with the production kernel, which is what we're using for this, FDO and PGO give us some of the best performance improvements in the networking code. We kind of, that's important to us. So we, and it actually gives us better performance than even just LTO. So if you run LTO, the performance for the PGO or FDO is going to be that much, it's like there's still a delta between them. It's going to be much better. We haven't yet tried LTO and PGO together because we've ran into some other topic which it's another talk on its own. So here are some numbers that I ran, and these are using the NetPerf test, and it's out there on the web somewhere. And basically, this is just running one of their example tests. And so you can see that the throughput is going to be much better with the PGO than without. And it looks like these numbers are kind of smallish, and they are, but this is, take into account that these are millions of bits per second on some of these tests here. So, and based on some of the sizing of the buffers and so on, you get different improvements over time. So the upshot basically with PGO is kind of, as I said, that you are going to get better performance out of it, and it's going to mirror pretty much what you're going to get from GCC FDO. And so the upshot here is that we can actually do that with Clang. It's kind of nice. All right, so back to you, Nick.
Thanks. Oh, enable my webcam here. Cool. And then, so on the flip side, so people were proactively asking in the chat is, it's interesting to be able to instrument a binary and collect the data from there, on certain architectures that have kind of hardware performance counters. Is there any way to leverage that to do kind of low overhead sampling based? And absolutely there is. So on the LLVM side, they call this auto FDO. I think there's discussions to rebrand that because it doesn't, it's not super catchy kind of thing. But what's interesting about this is you don't have to necessarily do a separate kind of training build and run it and then do a release build from that. You can just do kind of one build and sample that and kind of keep feeding in this profile for successive builds and collect it over and over again. But I think the thing that's a little tricky is it's very hard to get things to be quite as precise due to aggressive compiler optimizations. When you do samples, there is some loss of fidelity of where exactly did this come from in the source code kind of thing. So I think, there's kind of pros and cons of, which would we say is more precise? And there's definitely loss of fidelity on kind of both sides. So still open research question. Actually, there's even on the mailing lists, on the Llvm mailing list within the past month, we've had like discussions about this. But some of the benchmarks we had, I guess, curious measurements, but kind of doing system-wide traces, we'd see like how many cycles are we spending in the kernel, and auto FDO would give us a pretty good reduction across the board. One of the things we noticed is different microarchitectures though would give us kind of sometimes different results. The performance boost we'd see on x86, we wouldn't be able to quite get the same level out of using ETM on ARM64. So we're still going through and trying to analyze the data really and see, is something missing there? Is something broken? I don't know. But one of the things that's curious is someone found that you can actually use profiling data from an x86 build in roughly the same kernel version and actually use that in an ARM build. And you're not going to get data that says any of the ARM specific stuff is hot. But on the flip side, you're not going to get any annotation saying it's cold either. So you kind of just will get optimizations to generic C code, but not Arch specific stuff if you do that kind of stuff. So I kind of talked about that already. So I guess the big question I have really around upstreaming this is really around the notion of testing, right? Because LTO is really going to blow out build times for people. Thin LTO provides a significant speed up over full LTO if you have kind of the support for multiple cores. And in terms of profiling data, one of the things that we found is, this is kind of binary data. And if you check it in, it ends up being a lot of churn of binary data, which is kind of rough. So, I don't know if this is something we just say is config expert and not really do testing in CI It's not really great, but I don't know if folks have thoughts. But let's open it up to questions, because we have about 10 minutes left.
I think that's something that's rather interesting is the ability to, train your work, like train a specific workload. I mean, like Bill mentioned, networking is one of the most important things for the production kernel, and, being able to see the gains that you get out of that. And I think that, for certain people like me, for example, like I care a lot about compiling speeds, and so being able to run and instrument a kernel specifically based on that workload would be really, I think, beneficial to have even just the option to do. Whether or not it's, fully useful, you have to run the numbers and see. But I definitely think that getting this upstream and having it be available for people to kind of play around with, or just having some tree for people to start, poking at basically is I think super important.
I think one of the things that's exciting about this to me a little bit is that, like from machine learning, there's this notion of transfer learning is, if training is excessively expensive for some notion of expensive, what if someone pays that cost and then shares the benefits with other people? And one of the things we could do is, provide these binary samples somewhere where you could download them and reuse them in your build, right? Which I think might be interesting for people. And I think interesting question in the text chat from Brendan Gregg is, can someone please fix the docs for the auto FDO project? I agree wholeheartedly. That was something that was a little difficult for me as well, is finding the documentation there. I think in my experience, the documentation on the LLVM side was better discussing it, but I agree it would be more straightforward for us to actually have written up detailed steps of how do people reproduce this kind of thing. I think one question I'd be curious about is, right now we kind of have the patch set, at least the LTO patch set is carved up to say like, well, if it's Clang, you can enable LTO, and people have said like, well, are you trying to block it from working on GCC? And that's absolutely not the intention. The intention there is that we had a lot of compiler bugs to fix to enable all three of these. Like they tickled all kinds of dark corners of the tool chain, and I think more so we're just looking for someone on the GCC side to meet us, come to the table and meet us, and ensure that things work as well for them in case there are compiler bugs that people can find. Because at least in our experience, we had a lot of work to do. It wasn't just changes on the kernel side, for sure.
Hey, Nick, I just wanted to point out, BN mentioned that about the profile data, like this is going to be highly specific to most people's like configuration as well for the kernel. So it's probably likely that you won't want to carry that around in the regular Git tree for the kernel, and you would want it somewhere off to the side. But I could see sharing those Git repositories, and that's kind of how Android handles profile data itself, is that we have separate Git repositories, and then of course, since it's binary data, you can always just trash that whole Git repository and just link up a new one when you want to throw away a ton of ancient history. So yeah.
How much optimization work has gone into the LTO compiler backend in terms of like how, I know I've seen some recent things about Clang optimizations for compile time. I'm curious if there's been work on optimizing how scalable LTO is, how fast you can build a kernel, for example.
I don't know of any efforts. Even the profiling work is early days on our side. We have a talk coming up after the break that's starting to discuss that. But scalability of full LTO is definitely something that, you know, still something that's worthwhile to look at. And I think, you know, the larger your value of n is, like, where things that are accidentally quadratic become readily apparent. So, you know, full LTO can probably help us spot just general things in LLVM that are slow and could be optimized themselves.
Just a personal curiosity of mine. Clang, when building something by default without using LTO, has the option to save a report of all the optimization that it does on the source code. Does LTO have something similar in that regard to be able to debug issues easier?
Sorry, I was distracted in the chat. Can you repeat the question for me?
So when building without LTO, Clang has the option to save an optimization report. Does the same option also work for LTO or not?
Untested. I didn't even know that there is an optimization report. Do you happen to recall what the flag is off the top of your head?
I just Googled it and it's -f save optimization record.
I'm guessing it.
I don't know if this is actually going to be true or not, but a lot of the times you'll have internal flags, and there is a way to pass flags that are going to be triggered by, or are going to do things within the compiler that aren't necessarily -f flags. And you could do that in the linker as well. You could do like -m LLVM, and then whatever flag that might be. So that might be a way to do it. But like Nick said, I never tried it myself, and I don't know if it would actually work.
Yeah, I think just in general, there's a lot of things of, like, does this work when translated to LTO? And probably the safe answer is probably no, until someone tests it. Like, I think one of the issues is a lot of the -f flags were getting dropped. So, we had a discussion this past week on the mailing list about, like, kind of built-ins and, how that whole system feels kind of broken for pseudo freestanding environments. And for actually a long time, this was a big issue for us for LTO, was if you were not recording that, you don't have a built-in available in the IR, and then later doing an optimization that was a libcall optimization, suddenly you'd get linkage errors to functions that you never explicitly called yourself, but were never actually defined in the kernel.
Can you explain why with LTO the debug files get so big? My generated Debian packages are really, really huge.
I suspect there's a lot of type duplication going on, but it's something that we haven't looked into quite yet. I think we'll have to. I don't know if the issues around PA hole are similar or not here, if I even pronounced the name of the utility correct or not. But I'm going to wrap everything up here. Thanks for your time, everyone. We're going into a 15-minute break. Let's kind of curtail discussion or move to hack rooms or chat for follow-ups on these kind of things. That way, people have time to jump into other talks that maybe they're interested in, that they're scheduled for. So join us after the break, and we'll be talking about measuring compile times with Clang, Clang tidy, Clang format, and how some go to with outputs in other GNU C extensions. Thanks, everyone. Oh, good. It kept all our drawings. They're very important. I'm gonna go make a cup of coffee. Be back. Are my two Nathans online here? Can we test your microphone setups and camera?
Yeah, did things seem to be working?
Sounds good to me.
Cool.
Nathan, I know you tested your mic setup earlier. Can you test it again real quick for me?
Yeah, should be still good, hopefully.
Oh, and who's going first in the talk? I'll transfer presenter over to you.
I think my section's first, so I'll take it from the beginning.
All right, so you have presenter, so you should have controls now. You have to click. I don't think there's keyboard shortcuts for advancing the slides. And then if you scroll down, so you find the other Nathan in the users, if you click on him as a user and then you say make presenter, that will pass him the token so that he can advance the slides. So if you guys are going to flip back and forth, you have to manually pass that token. You can't have more than one presenter.
Where was the button that I needed to click for that?
If you click on his user name, and then it should be like a pop-up that says make presenter.
I only see start a private chat, so maybe you'll need to do that.
Okay, yeah, just let me know then when you want to hand over the slides, and I'll do that. Maybe because I'm moderator. I don't know. So I think we still have maybe 3 more minutes. Yeah. As a heads up, I think you guys only have, is it 15 minutes? So you need to go
20.
quick. 20, okay, yeah, you'll need to go quick. Yeah, don't worry about covering everything in the slides. You know, there's a live stream, people can see them kind of thing, so. And I'm hoping Arnd will jump in at some point with some of the work that he's been working on in this area. I think it's interesting, but maybe at the end when there's open questions. Hey guys, why don't you take it away?
All right, so we're going to be giving a presentation on performance with Clang, basically at compile time. So I'll just kind of dive right into it. It's not really a secret. LLVM and Clang specifically is slower than GCC. So I've kind of been experimenting with getting actual raw measurements for this, kind of what at a very high level, what we're looking at performance-wise between the two compilers, and maybe how LLVM technology, like LTO, PGO, stuff like that, can improve compile times just based on the instrumentation that you'll do kind of during build time. So I ran several tests for a couple different architectures with a tool called Hyperfine, which basically just runs commands in a loop and will kind of spit out some raw numbers with a standard deviation and stuff like that to see exactly how like what kind of numbers we're looking at. So just kind of a TLDR basically before I go over some of the numbers with some graphs. LLVM, even when you kind of optimize it to the full ability that we have, which would be with profile guided optimization and link time optimization, it's always slower for at least ARM64 and x86 when you're cross compiling for those platforms. On 32-bit ARM, PGO can currently get you some gains. I will note that these numbers that I'm about to show you were run before, were run with LLVM 11, so pre-release basically. I'm kind of trying to keep GCC and LLVM at their stable versions basically. And I will note that this is before some of the performance, like easy performance patches that we have in Clang 12 got backported to LLVM 11. So these numbers might be a little bit better currently. I have the full results that I've done and the testing scripts available if anybody wants to kind of experiment with those. But so to start off with kind of a 32-bit multi v7 def config build. So with just raw, so GCC 10.2, I would kind of consider the baseline basically. And then you'll kind of notice that there's a walk down here with different versions of LLVM. So for example, if you just like download LLVM, you build a release build, stuff like that, that's what I would consider just a stage 1 build. That's this first column here. And then you'll have a 2-stage build where you bootstrap an LLVM tool chain and then use that tool chain to build the same version of LLVM, would be like the 2-stage build. And then you have these different technologies that have been used at compile time to build LLVM. So for example, like when you use profile guided optimization, the script that I use, which is TC build, which is public on our GitHub, it will build a bunch of kernels essentially, and then you take that instrumented data and then you put it towards building LLVM, and then you'll get a fairly significant improvement in performance. This is basically the single biggest performance gain that you can get at compile time with LLVM basically. So the graphs are kind of similar between all of the different builds. I will also note that these are in seconds, just kind of as a information basically. And so kind of as you walk down, again, similar gains. You don't get a whole ton with just LTO by itself, but you do get a pretty significant step off with profile guided optimization. And again, same deal, with LTO and stuff, you don't get a whole ton of gains after that. I think that this is probably one of the biggest gaps, although x86 is also interesting as well. And that's kind of the next slide here. Again, you have a pretty significant uptick in that. And again, this is the biggest step off that you get. I will note that I didn't include in these slides kind of what the performance, like the compile time impact to LLVM is with these things. But it is, you get about, your build times increase by about 5 times. So like 5 times roughly with just profile guided optimization. That's between building the first stage of LLVM, building the instrumented compiler, compiling all the kernels, and then building your final compiler, which is like it's a 3-stage build basically is the way that we do it. I haven't done any sort of analysis into, what LTO would look like for GCC. I personally find it a lot easier to do stuff like that for LLVM just because it's a CMake system. So you just have to pass in a flag and it'll kind of just automatically do it for you. And then Josh, I have the system in the system that this was run on in the full results in one of the earlier slides. It's in the gist basically. I think it's I think it was a 2 CPU system. I think it was like some Xeon Golds or something. It was a total of 56 cores was that. So, and with that, I'll turn it over to Huck to kind of go over how we break this down basically. Like, what does this mean? How do we get a little bit more of a insight to this?
Yeah, so we've graphed the kernel compile times between GCC and Clang, and they essentially have the same distribution here, but Clang has a wider spread and seems to be slower on average. So in order to fix this, I've been profiling Clang builds with 2 separate profilers, the first of which is Linux perf. Since perf is sampling based, it reports functions that are commonly slow between all translation units. Many of these functions are already known to be slow, and but optimizing them would give us some pretty big performance wins. And the other profiler is Perfetto, which is an event-based profiler that uses code annotations in the compiler to generate traces. This is nice for more high-level trace data. We've done some amount of analysis and graphing based off of this data. It's also nice for finding compilation outliers, like, for example, weird front-end to back-end ratios. And you'll see later in the talk that there's some discussion of this. Fixing these seems to give smaller speedups in general than fixing the functions reported by Linux perf, but I think it's still worthwhile to look into. So in order to trace a whole build with perf, you would just run these commands. You can actually run perf record on an entire make invocation, and it will give you trace data that looks like this. So we see the top function currently is get file ID local. I believe this is slow around tracing, like finding source locations for macro expansion arguments. So we found some amount of low-hanging fruit using Linux perf. Most notably, there was redundant work around feature dependencies for inline ASM statements. So it would do a graph walk of CPU features. And this was taking up 13% of kernel builds. We've already fixed this one. And then the other one that seems to be notable is expensive calculations tracking macro argument source locations. This is what I was talking about on the last slide. And it doesn't seem super surprising that it took building the Linux kernel to find these slowdowns, because the Linux kernel's code is so unique. So as far as Perfetto goes, Perfetto traces have shareable links. So I've put 2 separate Perfetto traces down at the bottom of this slide. I would encourage people to go look at those. You can play around with them yourself. So we found some amount of interesting outliers from analyzing these traces, like million-character macro expansions that cause huge slowdowns in the front end for specific translation units, or repeated inlining of large functions causes repeated optimizations, which makes large slowdowns in the back end for some translation units. This is what a Perfetto trace looks like. You can see each translation unit is listed over on the left, and this is actually each compiler invocation. Oh, my alarm just went off. Okay, so this is like what a Perfetto trace looks like, and if you were to go expand one of these processes, you would see this breakdown between front end and back end, and you see for each source file that is being compiled, including files that are being included, it breaks down how much time is being spent compiling it, and then you see the back end. You can see exactly which optimization passes are taking time. So analyzing these traces gives you like a fair idea of what's actually going on. And then there's this query engine that I mentioned earlier. You can do somewhat interesting queries. Like here, I'm doing a query of sorting translation units based on their front end to back end ratio. And you can see there's like translation units that take 2 seconds in the front end and 5 milliseconds in the back end. And we've found some amount of interesting data doing this as well. So using the Perfetto data, we've generated a graph of like the front end to back end time spent in the compiler, and we've actually found that more time is being spent in the front end, which was somewhat surprising to us. It's not what we expected, but I think reducing the amount of work that the front end has to do will give us some pretty big speed ups for Clang. And then as far as future work goes, I think there's more to be done on analyzing these traces. Recently, I've just been trying to get the traces like actually working and doing some amount of analysis on them. But I think there's quite a bit more that could be analyzed here. And then as well, just making the front end or making less work for the front end to do. And then keeping track of like regressions and compile time. So for example, the CPU feature dependency graph walk was added to the compiler like a few months ago, and it just kind of slid under the radar. So it would be nice to keep track of when it happens. Cool. I'll open the floor for questions and general discussion now.
I would say I was immediately surprised by a lot of this research. In particular, we've heard a lot of feedback from the Rust compiler folks that LLVM was a significant source of compilation time, and for us, we kind of went in expecting that maybe LLVM would be the bulk of kind of the back end would be the bulk of time spent in builds, and we were kind of blown away by a lot of this work that kind of said, no, really the front end is what's killing us here. So I think, there's probably a lot of optimizations we can do around lexing and parsing that, like one of the things we've been discussing, I've been discussing with the Clang front end maintainer is, a lot of like high performance JITs try to lazily parse things, and could we lazily parse static inline functions, because maybe we have a bunch that are dead, and then actually do a control flow graph walk to generate the actual LLVM IR if it's actually used, kind of thing.
That would be a really interesting approach. I know that I see that on high performance JavaScript compilers. Yeah, if we can do a bare minimum tokenization and kind of brace matching, which of course with C has to interoperate with the preprocessor, but hopefully there aren't too many macros in the kernel that have unpaired braces.
Yeah, I mean, Clang already has like a skip ahead to the next matching brace method already good to go.
Okay.
And I would lean on that.
I'm curious, has there been any effort put into, recently there's some stuff in GCC trying to parallelize within one function. I'm sorry, not function, within one file. And I'm wondering how easy that would be to do in LLVM of here's a very large translation unit. Let me break that into 4 CPUs worth of compilation.
I think one of the tricky parts with that is I don't think LLVM was designed to be thread safe from day one. So I think there's serious concurrency issues there. And another part is for kernel builds, it may not be interesting to break up compilation of individual translation units into multiple cores, if you're already compiling multiple translation units in parallel. I don't know if anyone working on trying to multi-thread LLVM though.
I agree that would be that would not be likely to make an impact because the build system is pretty good at spreading things out. One thing I already mentioned in the chat, I had some analysis around recursive header usage where we include a bunch of headers and some of them turn into just massive amounts of code. There was one of the recent merge windows where we had factor 3 slowdown, and turned out that we had header files that just added like 30 megabytes of macro expansions to every compilation unit. And it seems that on average we get something like 10 megabytes. Still, I reduced this to something like 3 megabytes on average per source file, and I got something like 20 to 30% speed up of the kernel build just by rearranging all the headers and then changing all the source files to include all the headers that they no longer get implicitly, which is basically, I have to touch every single source file in the kernel. So this is a huge effort on the source, but it would, Clang would benefit hugely. GCC would probably also benefit to a lesser degree. So I hope that I can resume this work.
How much of that was automatable and how much of that was hand tuning on your part?
So I have multiple scripts. So it was probably about a week or two of full-time work figuring out what's going on. So I have one script that tells me for one kernel build which header files contribute the most to the overall compilation, like which header files are included how often during the kernel build and how big is the preprocessed source file for that header. And then I have another script that does pattern matching to just add explicit include statements for all the headers that files need when we no longer include them implicitly. One of the largest things was everything includes spin logs, and spin logs was already huge because it includes atomics and that includes lots of macros. So just getting spin logs out of every file made a huge difference, but then all the files that do need spin logs and don't include Linux spinlog.h, they have to be changed. And I think I have something like 200 regx header file pairs now where I just add random stuff. So there's an open question of how we can ever merge that. The most likely way would be to send my script to Torvalds and have him run the script just before the RC1 release at some merge window.
That would be great. And that's exactly what I was asking after, was if you had this reasonably automated, then sending that off to be run at that point would be great.
Yeah, so there's still maybe 1,000 files that need to be patched manually because the script doesn't catch them or the script gets it wrong. Possibly less than 1,000, but there's a huge number of changes that have to be done manually. There's a huge number of changes to the header files, and then there's the touch every file in the kernel thing that can be scripted.
I think one of the things that was most interesting to me was that you could use perf to trace child processes. So our invocations of perf record have been actually tracing the invocation of make, GNU make itself when building the kernel, and then getting aggregate of data across, most time spent in the compiler, which is good. But I think this workflow is repeatable whichever your tool chain is, which is probably interesting or useful for other people, like as a recipe to use as well. And I think one of the things I was most curious about, though, with perf is it seems to have the granularity of function level granularity, which for us gets a little tricky when there's aggressive inlining and already very large methods in Clang. Like you might point out this method was very slow, but it turns out the method is this big. So how do we bisect and chop that down? Is kind of an open question that I have. I don't know if anyone has experience with that.
Well, I manually look at the perf annotate output, and at some point I wrote some code that uses LBRs to annotate the hot path inside these giant functions. I am not sure what the current state of all that is, but that's basically where you're at.
Cool. Let's follow up on that. And Nathan and Miguel are going to talk a little bit about Clang Tidying Clang format. Who should I give presenter to?
Miguel.
Yeah. All
Cool.
right.
Take it away.
All right, so we will be talking about Clang Tidy, Clang Format, and other tools that come with the Clang tooling. I will be giving the first half, and then Nathan will give the other. How can I? Here. Yeah, sorry. Okay. So what is Clang tooling? As you know, Clang is one of the Llvm compilers, but it's also designed as a platform for building source level tools or platform or framework. It allows to do tools like syntax checking, code formatting, refactoring, etc. I will be going quick on some slides because we want to have discussions. And so for the kernel in particular, we have already quite a few tools like sparse, spatch, cosinel, checkpatch, etc. that were built basically by hand, as far as I know, the parser, etc. So Clang tooling, what allows is to build more of these kind of tools without having to deal with parsing the C code, without having to do this kind of work repeatedly. You don't have to support the C extensions, you don't have to write code for that, and you can easily access the EST. The Clang tooling gives you different interfaces for kind of different levels, high level, low level, depending on what kind of tool you want to write. And the first tool we are going to present is Clang Format, which is a simple tool. It's just a tool, I mean, simple in the sense that probably the implementation is not that simple, but simple conceptually. It's just to format code. C-like code is for C, C++, and quite a few other languages, not related directly to Clang. It has many rules and heuristics that you can configure and tweak to match the kernel or whatever, or all of the styles, so that it outputs what style of code you want. It's quite fast, fast enough to run it, for example, in your editor to format quickly a block of code, and it's good enough for everyday use. Some major companies, for example, I've seen on projects, for example, Llvm, I think uses Clang format to format all the C++ code in the project, or they are trying to achieve that. So it should be good enough for the kernel, let's say. So why would we like to have automatic code formatting in one way or another? The point basically is to avoid spending time on these kind of issues, not only writing the code, but also on the review side, because we spend a lot of time in the reviews on nitpicks and other small stuff that is not really important. So what we did is we configure already the kernel style or a kernel style that matches most of the kernel code, and it's already there. So you can see the .clang format file to see the rules, heuristics, etc. And you just run the tool and it will work. It's important to know that overriding this global style for particular subsystems that don't follow exactly let's say the common kernel style is possible. So for maintainers that need that is an option. So for someone that has not run something like this at any time, this is a trivial example, very small. You have some code that is not in the kernel style, and you simply run the tool to format that block into the kernel style. Know that even the indentation you cannot see there, but this will be a tab, not spaces, etc. So this function basically matches what we have right now in the kernel source. The common use cases for Clang format or things that we can do are things like reformatting blocks, as I said, which is useful when you refactor code or when you indent code because you put it in a loop or whatever, and you need to keep with the line length. So you don't need to, rearrange all the parameters in the code, etc., to fit in the 80 or 80-ish code limit. It can also, of course, reformat full files, sort the includes, align the variable logs or the macros. You don't need to align all the backslashes one by one when you edit a macro. It can reflow comments as well, and a few other things. But for the kernel, in particular, Clang provides a script that can reformat patches, unify these patches. And this is useful for both maintainers and authors. Authors that write the code is useful to, if you are not sure about the kernel style, you can just run the tool on, and also it's useful for maintainers because it allows us to review it quickly. Personally, I just apply if I need to do that, I apply the patch with Git, and then I run Clang format. So I don't use the script, but it's an option you have. It can be very useful for the kernel because we have a quite seizable code base. So it's useful for code dumps. These kind of, big systems that are developed out of tree, and then they are submitted at once at the kernel, and because they were developed in a company, for example, and they follow another style. So for people submitting this kind of code, it can be very useful. Even if the style that Clang format outputs is not perfect, it's very useful to do it at once. However many lines you have of code, for example, you have 10,000 lines of code, you just 100,000, you just format them all at once. And it's also useful to lower the barrier of entry a bit to the kernel, in the sense that, for newcomers, or even not newcomers or inexperienced people, but also for experienced people that switch from one project to another, and each project has different code styles, it's useful to just not have to remember all the rules in your head. Next, how to run it, I put that it's very easy. You have support for many kinds of editors, either officially or third-party plugins. There is support for basically everything out there. The example I saw there is rewriting this would rewrite that file. So you run it, and then you just, for example, do git diff to see the differences, and if you like the code or not. You will see, if you do this with many kernel files, you will see that the output is not perfect, and some things are, objectively are worse because they are done with heuristics, and it's not, sometimes it's not as regular or as you could, or as a human would write it. But you have to always think about the advantage of not having to do it yourself. What I wanted to discuss, or the slide that is important, is the proposal or the plan for Clang format. So for the short term, I wanted to have more devs aware of Clang format, more devs to use it in the kernel, and then starting from that, have maintainers of either a small or big subsystems start formatting their subsystem with it. Perhaps not automatically, but have it, let's say, more or less widespread, so that we can convert on the sorry, I was reading the chat for a moment. So we have to try to convert to the slightly different code that we have. It would be nice to have one style in all the kernel. And long term, this is a bit idealistic if you want, but it would be nice to have the kernel code automatically formatted everywhere. Perhaps not everywhere, but almost everywhere. At that point, we wouldn't need any more reviews of a style. We wouldn't have to discuss this in the mailing list. We could even go ahead and remove the code and style documentation file to just forget about it. And yeah, this is a bit ideal. We would probably need a bit of support from Clang format from the tool itself. Perhaps it's on my plan as well to when I have some free time, or if someone else wants to do it, to go into Clang format and both add the kernel style to it, built in, and also to have some things that are different and Clang format does not support currently. That would be nice to have even less differences between what the output, what the tool outputs and the actual code that we have right now. So that's basically it. We have here further information for that. I wrote a quick kernel guide when I introduced this a year or 2 years ago. You can read it in documentation process, and the official documentation, you have it there. Well, in general, if you want later, after Nathan's part, we can discuss about what maintainers may think about doing that for all the kernel, etc. So I give it to Nathan.
Nathan, you're muted.
Oh, okay, cool. So I'm talking about Clang Tidy. Clang Tidy is self-described as a linter that can identify style violations, interface misuse, and bugs deduced by static analysis. It's generally used to write code-based specific checks. I think calling Clang Tidy a linter is a bit of a disservice. It hooks into Clang's front-end actions, so it has the full power of Clang's front-end behind it. Almost any Clang front-end warning could probably be re-implemented as a Clang Tidy check. So as far as Clang Tidy checks go, they consist of two parts: an AST matcher, which looks for an AST pattern, or a node pattern in the AST, and then a check callback, which runs like the meat of the check. If you wanted to write your own check, you would use the pattern matcher DSL exposed by Clang. Here's like an example pattern. So we're looking for calls where the function name is error pointer, and it has the direct parent of this call is a compound statement. So a compound statement is explicitly not an if statement or an assignment. So essentially, we're looking for calls to error pointer where we're just throwing away the return value. So there's like a huge list of different like patterns that you can match with the DSL. I would encourage people to go look at the libAST matcher reference. It's pretty big. And then you would just write the check callback. So the pattern matcher hands off the matched AST nodes to the check callback, and it includes all of the compilation metadata, so you can just use like the full power of Clang's front end to write your check. We're in the process of adding Clang Tidy as a make target. So to run Clang Tidy, you just say make Clang Tidy. Fairly useful. And then there's also the Clang Static Analyzer, which is a separate tool that can be invoked through Clang Tidy. It uses symbolic execution to find path-sensitive bugs. It's a lot more complex than Clang Tidy, but very useful as well. If you want to run the Clang Analyzer, we're also adding make target for that to give you text reports, and then you can also generate HTML reports using this utility called Kbuild. So if you run Kbuild, you will get output that looks essentially like this. You can see like all of the different bug types detected by the Clang Analyzer. This is actually like a build of the kernel that I did yesterday. And then you can see like this is what one of the Clang Analyzer like warnings looks like. You can see like it follows branches and does like smart stuff using static analysis. And then as far as future work, I think we need more Clang Tidy Linux kernel checks. So currently, I think there's only one Linux kernel specific check, and I'd like to like open the floor to see if anybody has ideas for new checks to add to Clang Tidy. Yeah.
Nathan,
or I guess questions as well.
Didn't you write a check related to forgetting to re-enable interrupts?
Yeah, so I don't think that one ever actually went into Clang Tidy, but it's essentially like if you have mismatched calls to disable and enable interrupts, then it would give a warning. I think Clang Tidy is like super powerful, so I'd encourage people to come up with any possible way we could use it.
I think in particular, a lot of the times that we get requests for warnings that are more specific to a code base and not generally useful to a lot of C code, C projects in general, I think Clang Tidy is really like the perfect fit for implementing code base specific warnings. An interesting use case for it.
Just wanted to mention that there's also the Clang query tool. You don't actually need to write code to run Clang Tidy check. You can just write a simple query language with the Clang query tool and get the same results.
I'll mention another use case that I have for this is we've been running into issues with Gen K sims, for instance. So I think it's interesting to be able to try to leverage a production C parser that can actually parse things correctly. So I think what's interesting with the Clang Tidy stuff is it gives you, the matchers are based on matching AST nodes, but from there you really have the full access to the rest of Clang. So if you want, you can then go and construct a control float graph based on your current expression kind of thing, and then do like more interesting analysis off of that. It's very powerful.
I actually wrote a Clang Tidy Linux kernel checker. The very big pitfall I had right there was the fact that it's very easy to write a slow checker because you can write a query to get all the variables, then all the functions that use all the variables, and filter those functions and so on and so forth. It's very easy to get into very complex algorithms that really slow it down. Just throwing it out there.
I guess one question we have is what would be useful for us to implement? Maybe some kernel developers, like if there's something that they run into often, is there possible ideas that we could build the static analysis for? It's something that we're interested in.
My guess is functions which most of the time need to have the return value checked, and it's not checked in the source code. That's something that could maybe be very easily implemented and very easily checked.
Function attributes for must check. There's some issues with that with GNU C statement expressions. Actually, that can get lost on the final statement of GNU C statement expressions is a known issue.
The currently existing Clang Tidy Linux kernel check is exactly that. It's checking to make sure that we check return values.
Does it also work for macros?
I have not tested it, but I assume that it does.
We have a bunch of different checking tools like Sparse and Smatch and to some degree Coccinelle. So anything those do, you could probably do here as well. The question is whether we want to duplicate any of them or we're looking for things that they don't do yet.
The major issue with those other tools, though, is they aren't built with compiler technology, so they're re-implementing the grammar and tokenizers. Whereas at least Clang Tidy and Clang Format and such, Clang Analyzer, they use the same front end as the compiler.
I would also mention how easy it is to write a Clang Tidy check. You basically just have to have basic knowledge of C++.
For fun, a poll on using Clang Format on the subsystem or not. I mean, churn is always brought up, but hurry up, get your answers in, and then we're going to move over to Bill's talk. And again, the poll's not limited to just maintainers, so.
Yeah. Same thing.
Okay, Bill, why don't you take it away? No audio, Bill. No, I can't. You want to try dialing in on your phone and do audio on the phone? I can help advance the slides maybe. No, no audio. Hey, that's working. There you go.
Can you hear me now?
Yep.
Okay, great. All right. So anyway, as you didn't hear me say, we developed a new feature. Actually, we just extended a current feature in Asm GoTo. Nick, could you share the slides again, please? Thank you. So anyway, to give a brief overview of what Asm GoTo is, I'm sure a lot of people know, but just kind of do a general update. Asm GoTo allows assembly code to jump to one or more C labels. And kind of the motivating example of this, or why this was created in the first place, is let's say that you wanted to do tracing on a function or a section of code or whatever, but you don't want to trace it all the time. So in the common case where you're not tracing it all the time, you want it to go as fast as possible. So you can create a no op here, and then at runtime, if you decide that you want to trace it, you can patch up the code, do that jump to the trace, and then go on your merry way with tracing the code there. So it's kind of a way to get around something that could take a long time, if you just put it in there. But for GCC, they weren't able to support outputs from the Asm GoTo, and that's due to an internal restriction of GCC. Basically, the control transfer instructions, which Clang calls terminators, I'll be using that in the future, they cannot have outputs, basically, not in their intermediate representation. So Clang is able to support outputs on their terminating instructions. And so, in fact, that's how we implement exception handling, or at least model it in our IR. So when we got into the gritty minds of implementing this feature, we kind of quickly realized that we could only support this on the fall-through path. My initial idea was to support outputs on all of the various different paths. But supporting it on the exceptional paths were very, very different. It's not clear how we can handle it. And one of the reasons why is kind of what I put here. So in a fee node, for people who are not familiar with compilers, in the static single assignment, which is a form that Clang uses for the intermediate representation. If you have two values coming in from different branches and they're assigned to the same variable, I'm waving my hands here because SSA doesn't have the same variables, but you have to choose one or the other of them that are coming in. Well, you represent that with a pseudo instruction called a fee node. And that just basically says, there's a value coming in from these two branches. We're going to pretend that we have one of the values here, and we'll fix it up later. It waves his hands a bit. So that's all fine and good, but on the indirect branches, they have taken the address of the that block, and that address can be used as data within the asm_goto block itself. So having them jump to the same address in the intermediate representation, you would need to put a fee node in there, and then resolving that fee node it's just not clear how we can achieve that without inserting some awful hacks that would just slow everything down and make this completely useless. So because of that, and because we really couldn't resolve this engineering issue, we just decided that fall-through path was the only way to go. So why would this feature be useful at all? So if you think about it, kind of as the initial write-up or initial motivating example pointed out, an asm_goto block is basically just, it just wants to be a regular block, and it would fall through to the bottom just like a regular asm block, and go on its merry way. And this is the default behavior that we are hopefully going to be doing the majority of the time. Well, regular asm blocks have outputs, and asm blocks themselves are used, for a lot of things, but primarily for optimizations. And so you still want to maintain all of the behaviors of an asm block as much as you can in order to get the full benefits of the asm block. So there are some benefits to that. It basically has the same behaviors, but you no longer now, and because of that, you no longer have to use memory for the outputs, except on the indirect branches still, if you're going to be doing that. And it can improve the programmer's ability to reuse labels as exceptional cases. It's like if you have a macro and you can pass in like a label, and then it can be used in multiple places within there, and kind of like in an example like the unsafe get user, you can use that in multiple places and be able to optimize for the common case and get something for the uncommon case. Okay, so there are a couple of ambiguous cases that may come up. So like, for instance, if you have multiple asm_goto statements and they have the same target address, but their outputs are not mutually satisfiable, the constraints at least. So in normal code, you would have something in the middle saying that, or like a little block in the middle that would handle all of that, and then it would go on and combine, and everything would be hunky-dory. But I'm sorry, but it may, I personally think that should never happen, because I believe that an asm_goto block should always have its own independent block that is falling down to at least the default. But that's not something that you can really guarantee because of all the transformations that the compiler does. Also, if you jump to a label outside or where the variable is out of scope, you might get garbage in there. So you could have something disgusting like this example that I put here, where you jump to a label and the label y or x doesn't have a real value yet, so y kind of gets a junk value at that point. So
that's exactly the kind of code that Linus wrote. Actually, trying this out, I was like, "Oh my God, an if zero, what's going on here?" Shocking.
Yeah, it's pretty awful. So basically, this code is. I mean, it kind of still exists with just regular Asm-Goto actually, but you know, it's kind of a gross situation. It's kind of yeah. So just to kind of get down to the nitty-gritty of the design details, and I'll try and speed this up a bit. Clang allows terminating instructions to have outputs, like I mentioned, the exception handling. The intermediate representation, the actual LLVM representation, is converted into what's called machine IR, and that's a very much looser representation. The Asm-Goto's normal, or the normal representation was represented as a terminator in the MIR, but that didn't really fit well with the backend restrictions once we added outputs to the Asm-Goto. And because you can't have non-terminators after a terminator, you can have multiple terminators in the same block, but you can't have, like, you know, Asm-Goto terminator and then like moves into virtual registers for all the output variables, so they can be you know, live outside of the block and then go on. So one way that we could get rid of that was to create a block underneath that would be the fall through block, and then place the spills in there. But that also violates another invariant that the backend kind of holds dear, which is that the live in analysis isn't run until late in the MIR process. And so you can't really have the live in values on those blocks because people, the passes really aren't expecting it. So we ultimately decided that the Asm-Goto representation in the MIR just shouldn't be a terminator at all. You know, as I mentioned, it's supposed to just be a fall-through block with exceptional cases kind of over here. So it can, making it in the IR block, or, you know, just kind of in the center of the IR block, allows it to fall through in the normal case, and we can insert the instructions in and after. We have to be careful, though, that on the default path, the variables are defined in the correct places, but on the indirect paths, all of the variables that are used on the indirect paths have to be defined before the Asm-Goto, of course. So there has been a configuration option inserted into Llvm, or I'm sorry, Linux right now. However, I don't believe there are any plumbing that are using it at the moment. Okay, so I don't have a lot of time left, but basically the RFC here is to have, it's mutually beneficial for both GCC and the Clang communities to collaborate on Linux support. We both have great ideas. We both have our own tools, and we bring different things to the table. And so it can be a really good use of our time to collaborate a lot more. And Nick has created a renewed effort to make Clang a first-class citizen in the Linux world. And there's a link on here for that. So anyway, thank you for listening to me. And if you have any questions.
Thanks for all the work that went into this, Bill. Yeah, I really envision that, you know, maybe this is one of the first things we could discuss on the potential new mailing list is, you know, maybe GCC folks could help us find more ambiguous cases, or could start off with some of our test cases to kind of work through and build up to, you know, having a bug-free code gen and use of this in the kernel. And, you know, we're happy to share patches actually that do make use of this. You know, we do have them in hand kind of thing. It's just a question of, you know, which release do we land them in right now kind of thing. any other questions? Otherwise, I think we'll be going on a 15-minute break. I want to see what Seger is typing here.
Oh.
So Seger, just for the video stream, it says GCC can have outputs on jump instructions just fine. The restriction is that there cannot be output reloads. This means in particular that all outputs have to allow memory.
I can talk as well.
Go for it.
Okay. There can be outputs on jump instructions just fine, but there cannot be output reloads because there's no place to place them in general. Which means that any output has to allow memory as well. But since in inline assembly, you cannot have instruction alternatives, it means that your only alternative for the output will be memory.
Yeah, okay.
Which means that there's no point to this at all.
Okay, yeah, I'm basically going off of what was mentioned in the documentation, but it's a good point. Thank you.
Yes.
Cool. All right, let's go on break. See everyone in 15 minutes, and we're going to have a presentation on some machine learning and statistical analysis of build failures, how we can improve and speed up kind of builds or offload builds to microservices, and then finally, what are the future requirements on the various kernel CI systems with Clang kind of thing. So, thanks so much, Bill, and we'll see everyone again in 13 minutes. one of the things you can try is either a browser restart. I've had to deal with machine restarts, help me out. Otherwise, dial in on 4G if you can, audio on a phone. Different setups with network address translation causing issues for folks. Use of proxy servers and VPNs has also been problematic for people for the conference.
Okay.
Hey, sounds good.
Sounds good?
Yep.
Okay, nice. Okay. Is the volume okay?
Yeah, sounds great.
Okay, because the microphone is quite efficient, but you have to be close to the microphone. Apparently.
Yeah, those condenser mics are incredible at like how well they're able to eliminate background noise, but sometimes that means you almost like mouth is directly on the microphone.
Yes, something like that. Good. So how does it work? You have the slides, right? And
yep. So I'll in a little. Well, I'm letting everyone have fun drawing, and in a little bit I will make your slides the ones that are up, and then I'm going to transfer you the presenter token, and then you can click kind of left and right at the bottom. There'll be controls for you to advance your slides, kind of thing. So I'll pop in with video feed just for 5, 3, and 1 minute warnings, kind of thing. So maybe around 5 minutes, try to have your slides wrapped up at least for discussion, if not sooner, kind of thing. So
yeah, exactly. Yeah. Okay. I have seen that you can make a poll, right?
Yep.
I don't know how to do that.
Yeah. So when I transfer presenter to you, so let's try that real quick, actually.
Okay.
So
it can be fun, right?
Yeah. Okay, so I made you presenter. So in the bottom left, you should have a blue plus. And if you click on that, you can say start new poll. And in there, there's kind of a predefined like set of answers, or you can do a custom poll kind of thing. And one warning that I found out with the poll in the last talk is if the options are too long, it becomes very difficult to read them.
Okay. Okay, I can try. Okay. You have a blue
Try something
button,
now. Go for it.
Yeah, okay. I will try.
Don't forget to click publish too. That way
Yeah,
it'll show it. You can see who answers which way. So as a heads up to people, they're not kind of private, but when you publish, it's still private.
Okay. Click here. I have impression that I cannot customize and basically write down the question.
You can. I think there's well, it doesn't show you the question. You can customize the answers.
Yes.
But it's limited, I think, to 5 answers at the max.
Okay. Please see. Okay.
All right, I'm going to take back presenter just to clear this in a little bit and upload the slides. Daniel, do you have any beer that you can share? Okay, who's trolling us in the drawing? Who wrote I heart C#? Get out. Okay, folks, I'm going to turn off the whiteboard. Let's take a screenshot of this. I can remember the hotkey in Chrome OS. Beautiful. Okay, this will be preserved in stone.
Oh, it's working.
Okay, we're going to start in 2 minutes, but I'll make you presenter now.
Mm-hmm. And can I progress myself?
Yep.
The slides? Yeah. Okay, great. Thank you very much. Okay, I won't use a poll after all. I will use the chat.
Not saying I'm against C#. I think all languages have their pros and cons, kind of thing. But we'll give it another minute, and then maybe we'll get some stragglers joining, and then you can take it away.
Okay. Should we start? Yeah, okay. Thank you very much. Thank you for the invitation, Nick. So I'm Mathieu Hacher. I'm associate professor at University of Rennes. And yeah, usually I'm considering configurable system, and yeah, Linux is a kind of extreme case, right? There are so many options, and it evolves so fast that it's kind of fascinating and also challenging. So in this talk, I will briefly present what we are doing in research, explain the idea, and then I will move with the kind of objective we have, which is to use configuration failures with C-Lang. So I mean failures that pop up with C-Lang-based building of the kernel, to then try to improve C-Lang itself. So it's an idea, right? And I really want to discuss with your community. So the Linux kernel is quite big system, right? There are 15K options, and it doesn't keep it keeps growing at every release, and the number of configuration is really huge. And we are particularly interested in configuration of Linux. And so I really mean all kinds of configuration, not only the default configuration, but also the random one. And we are interested by, at the moment, 3 things. One is to fix or find configuration bugs, right? So basically, you compile a random configuration, and sometimes there is a failure, and sometimes you want to fix bugs, right? And we want to systematize the process, meaning finding as configuration bugs as possible, provide or synthesize fix, and prevent. I will explain what I mean here. The second research direction we are interested in is to predict the kernel size out of a configuration. So the size of a kernel, I mean VM Linux or compressed size, it varies a lot. So in our experiments, we show that it can go from 7 megabytes to 1.8 gigabytes. So the range of value is quite important. And we want to predict the kernel size without compiling the configuration, just by guessing with some machine learning technique. Another research direction is to predict the compilation time of a configuration, because again, it can vary a lot depending on what you're using. And we have a tool, a specific tool. So it could well be kernel CI to build kernels, but in XML we have some specifics. But the 2 projects are clearly related. So we made some experiments, right, in the configuration space, and sometimes configuration fail. Sometimes they do build and everything is nice, but sometimes they do fail. So I have some fresh results. You can see different versions of the Linux kernel, the number of builds we consider, and we report on the number of failure. It means that you have a .config file that you get with make run config on this specific architecture. You build it with a specific compiler, not C-long GCC, and yeah, sometimes you get failures. So the percentage is here. These numbers has to be taken with caution, just to show that they are failures, basically. Right? So we are analyzing it, and we will report on the community here. And one observation that is important to make is that not all failures are due to an actual bug in the kernel. Sometimes it's due to the building environment. So I will explain what I mean here. And in this case, it can be seen as a kind of false positive, right? It's not due to the source code of the kernel, but on the way you compile it. Another observation is that some failures are due to the same bugs. So the number of failures is one indicator, but in fact, you can group together some failures and it leads to the same bug. So sometimes failures repeat again and again. That's why we have such big number, especially for version 4.13, when we analyze deeply all failures and we found that, in fact, they are related to a very few bugs. So it's ongoing, right? And what I want to show here is that some configuration fails, and you have to do something, right? And so we do that in the large, and we gather numerous data. We have a huge database, and yeah, our basic idea is to try to understand what caused a failure. Not only at the source code level, but mostly at the configuration level, meaning that what combination of options leads to the failure. And if you look at this very simplistic example, you can see a kind of pattern in the data, is that when you deactivate generic allocator and you activate DRM TTM, you have a kind of failure that pops up. So that's something you can exploit to track the responsible options of the failure, and you can do that in the large. In fact, it's a supervised classification problem. Supervised because you have the features of your problem, which are configuration options of the kernel. And it's a classification because you want to determine whether it builds or fail, and the class is build fail. So with this kind of problem, you have many algorithms that have been developed in the machine learning community. And one interesting stuff is that you have some of them that are quite interpretable, meaning that you can really see what the learning model has inferred. So in this example, yeah, we get that generic allocator and DRM VBox video leads to a failure. And there are also options here that also leads to the failure. So that's the process, and like that we can pinpoint faulty combination of options, and we believe it's really useful for locating a bug, for understanding it, and then developers, I mean humans, but machines can certainly provide more easily a fix. And it can also be used to prevent failures to pop out again. Because if you know that some combination of options necessarily lead to a failure, you can deactivate it a priori. So basically, then you can explore the configuration space without this combination of options, and you save some cost. So we apply this approach, and it gives quite accurate results. And it's even more effective when you analyze the logs messages, the failure messaging, and you cluster them together, and then you try to predict the kind of failure that the configuration options are associated to. Okay, so right now I haven't talked about Clang, but I will now. So when you have a failure, basically two questions can be asked. Is it a bug of the Linux kernel? Or is it a bug of the compilation environment? If you look carefully at the decision tree of the previous slide, the two first options, and I think even the three first options, cause a lot of failure. And an in-depth analysis shows that it was due to our building environment that wasn't able to offer the tooling dependencies to actually build these very specific options. So in a sense, it's not a real bug of the kernel. It's due to the compilation environment. So when you have identified that, and most probably humans can do that, you can prevent it, as I have explained, to avoid costly and unnecessary build, because you know that it will anyway lead to a failure. Of course, there are cases in which it's a real Linux kernel bug, and you can pinpoint responsible options. So my main point is that sometimes the failure is due to the compilation environment. So sometimes it's due to the Linux documentation, because for such option it was really unclear, and there was some commits that fix this lack of documentation. Sometimes it's due to the continuous integration service. So XML, not kernel CI, right? Because kernel CI is great. And sometimes it's maybe a compiler bug in a broad sense. So it can be due to GCC, but it can also be due maybe to C-long specifics, right? So that's the idea, and that's my claim is that configuration failures can help. That's kind of surprising because configuration failures are normally a problem, right? But actually, you can use this problem to further understand another problem, which is the C-long support in the Linux kernel. So basically, configuration failures, when compiled with C-long, could be very useful to pinpoint C-long specific issue. So when you compile a .config with C-long, you can compare with GCC and see what's going on, if there is the same build status. If it fails in both cases, okay. But if it fails only with Clang and not GCC, you have to wonder why. And also, we can certainly identify problematic combination of options through statistical learning, as I have explained, to avoid duplication of bug report, and to prevent some combination of options that will anyway lead to failure, so that you can then explore further the configuration space. And also by pinpointing problematic combination of options, maybe you can also better understand C-lang related bugs, because you know where the problem potentially comes from. So I would argue that it can help improving C-lang. So my idea, and why I say my, in fact, actually, I haven't said that in the beginning, it's really a joint work with many colleagues at REN. The idea is to perform a large-scale compilation of random config with C-lang, not GCC, as I have done in other experiments. And the idea would be to collect some failures, because I suspect there will be some failures. And then, and that's why I need your help here, I'm wondering which C-lang version should I use, which architecture of the Linux kernel should I target, which Linux version to focus on, which configuration. I say run config, but maybe it's a run config which is a bit constrained when you deactivate some options because you know that they are not that interesting. And on this configuration, you can make several observations actually. So you can have a look at the build status and compare it with GCC, let's say. But you can have a look also at warnings to see if there are more warnings or not. You can have a look at the kernel size. I'm really interested to know if C-lang build kernels have a different size than GCC. I'm pretty sure it is the case. And same for compilation time. So chat and community, we have to formulate an hypothesis. What's the percentage of build failures you estimate that will pop up with C-lang? With GCC, it was around 1.5% on run config. If we do the same experiment with C-lang, what's your expectation? Please put some numbers in the chat.
100%.
Seriously.
No, so that's okay, so
much, yeah, much more than GCC, right? Yep. Okay, I'll say 1.6. Yeah, a slightly more. Okay. Actually, we don't know, right? We have to do that. So I have put some questions. So if you have some specific idea, you can discuss that with me after all.
Config builds, so I pretty much have a good idea what the actual failure rate is, and most bugs are the same. It's very small,
okay.
Compiler specific.
Okay, so you expect very
x86 and ARM64. As soon as you go to other architectures, you would have a much higher failure rate using Clang. On ARM32, lots of different options fail, and on all of the minor architectures that Clang even supports, yeah, chances of getting a working kernel out are still fairly low.
Okay. So what are your suggestions about the targeted architecture?
It depends on what you want to do. If you want to do statistics on working kernels, then do x86 and ARM64. If you want to find interesting bugs, then do the other architectures that are known to have a lot of bugs.
Okay. Okay, so yeah, it seems there is a consensus that we should target more lighter tested architecture, as Nathan stated, because x86 seems well tested, right?
Cool. Yeah, let's certainly follow up. But I think, you know, we're definitely interested on the Clang side is how can we leverage this research to help us start finding bugs? Because people ask us, you know, does the kernel build with Clang? And I think to myself, your statistics about 10 to the 6,000 configurations, and I think probably a good handful of those are broken. So thank you very much, Professor.
I'm interested in the size and compile speed based on configuration, because that's what I'm not testing.
Yeah.
Cool. Right. Would you like to take over from here, Dan?
Yeah. Hi. You hear me okay? Great. Thanks for having me. I'm going to get started right away. We're here to talk about TuxMake and TuxBuild. So how often are you involved in a thread that looks something like this? Hi, I've got a build failure, and maybe someone else looks at it and they can't reproduce it. And so they ask, what config did you use? And they may reply def config, and they say, well, what tool chain? And you may say GCC. And you might say, well, what architecture? And they say MIPS. And well, you didn't try that one. Or they might say, well, I have this environmental variable set that I forgot to mention, or some other thing that makes it hard to reproduce across mailing lists. So here's some problems in the kernel building community that we see that we're trying to address here. So build environments are half of the build. So you have your source code, but then you also have the environment that the build runs in. They're not reproducible in Linux, and they're not portable. So your system is different than mine, and there may be minor differences that account for variants that actually matter. Another problem is that when you start talking about, and this is what the professor was just talking about, when you take all the tool chains times all the architectures times all the configs times all the build targets in the tree, you have a non-trivial set of matrix of combinations to deal with. And additionally, each of those can introduce user space or environmental requirements. In addition, managing build artifacts can be messy. Dealing with copying files from one place to another, making them available to a CI system or to some external system. Automating of all of that is usually non-portable. It's usually do-it-yourself. There's a lot of people that have spent a lot of time writing code to try to automate these things. And finally, your build coverage is generally eventually limited by either build capacity or by the amount of effort you're willing to put into supporting all of those different combinations of things. So what if we could version build environment similar to how we version Linux source code? And what if we weren't as constrained by build capacity? So first, I'd like to introduce TuxMake. This is an open source Python project that is a thin wrapper around Linux kernel builds, and it provides portable and hermetic Docker-based build environments. So this lets us, you and I, build the exact same in the exact same build environment. So these are pristine build containers. They're based on Debian, and they contain only the things that the kernel build requires. There's no external constraints. This provides a common interface to building across architectures, toolchains, configs, and targets. And it does some nice things like collect your artifacts for you. It collects metadata for you about your build. And it treats the kernel source actually as read-only. So you don't actually even need to write into the kernel tree. Everything is done to an external output directory. We wrote it to be high-quality, reliable software, so it's 100% unit integration tested. It was written by Antonio Cercerio, who's on the call here and can answer questions in chat while I talk a little bit more about this. So this is a serious project for us. So how does it work? Here's a screenshot. If you just go into a Linux tree and type tuxmake, it's going to do something. It's going to build based on the native architecture that you're running on. It's going to do a def config build. It's going to detect your CPUs. So basically, it's going to run make def config, make modules if necessary, make DTBs if necessary, and it's doing this without Docker. So by default, it doesn't use Docker. It'll detect a toolchain. I think it defaults to GCC. But then if you do runtime Docker, now what it's going to do is it's going to do that same logic, but it's going to pull a container from tuxmake from Docker Hub. So now your build is transparently going to happen in the Docker environment rather than in your local environment. So it's going to mount in your source tree. It's going to mount in the output directory, and it's going to perform the build. Each make command happens in its own ephemeral Docker run. Of course, we support more options than just that. So you can specify your toolchain, you can specify your target architecture, and if you specify Docker, it's going to download the container for that combination and build in that specific container for you. Okay, so build artifacts. This is an example of what it does by default, and it will create a directory and put all of your build artifacts in that directory. This is an example of the metadata file, the top of the metadata file. So it collects a bunch of the data about the build environment and the build itself in this metadata file. It makes it easy for consuming by JSON. This shows the combination of support matrix that tuxmake currently supports, but we really wrote it to be extensible. So this is just sort of an example. This is what it actually supports today. But it's easy to add support for new architectures and new tool chains. And so what we hope is that this helps solve that problem I started off with, which if you saw a mailing list post that said something like this, even if you don't use tuxmake, the tuxmake command should give you everything you need to know to reproduce a build that somebody else created. Okay, so getting started. This is a brand new project. We just wrote it in the last couple of months. You can install it with pip. Debian packages are coming soon, and you can find the project at gitlab.com/Linaro. And the second project I want to talk about is Kbuild. Kbuild is a fully managed service by Linaro, and we're trying to solve the build capacity problem with Kbuild. So this is an API that allows you to submit a build request to the API, and it will build all of the builds that are requested at scale in parallel. So it's not serializing all the builds one-to-one, it's building them all in parallel. It's easy to use, it's easy to integrate with CI and developer workflows. It's been used in production by LKFT, the testing project, since January. It supports individual builds as well as build sets, and it has similar interface and similar combinations supported as to tuxmake in terms of GCC, Clang, and architectures. So an example of running Kbuild, you specify the Git repo that you want to build, the Git reference or SHA that you want to build, the architecture, the config, and the toolchain. Your build is done by the service, and then the artifacts are available to you at a URL that it provides. This is what the artifact hosting looks like. So it's just a web page that you get where you can download your individual build artifacts and build log and the metadata about the build, etc. But critically, it supports build sets. So you can define a number of builds, 10, 100, and you can ask Kbuild to build all of those. And so in this case, we're defining a number of architectures, a number of tool chains, and tiny config, but that could be def config or almod config. It supports fragments and things like that as well. And so if you were to submit that build set, you would see output that looks something like this, where all of them get submitted in parallel and returned in parallel. So here's an example of it integrated with GitLab CI. This is a kernel maintainer who uses Kbuild to validate his tree. He does 268 builds, including all mod config and all no config for 4 architectures. And lately it's been finishing in less than 20 minutes. That's only because it's well cached. If it's not well cached, it takes longer. So there's some luck of the draw there. And there's a link there if you want to see the details of that. Likewise, here is LKFT's current GitLab pipeline, where you see the builds that happen on the left-hand side there. Those are all Tux builds. Some of them are build sets, some of them are individual builds, but the time it takes to do the builds is basically constant. It takes about 15 minutes because they all happen in parallel. So if you have more builds or fewer builds, it doesn't really matter. They all happen at the same time. So like I said, Kbuild is a fully managed service by Linaro. The CLI is open source, but the implementation, the cloud orchestration stuff is private. Its current status is early access, so you can email us if you're interested in using this, and you can find more information at its GitLab project. And that's the end of my slides, Nick. I guess I can open the floor for questions, and I haven't been watching chat, so.
Yeah, sorry. Non-monotonically increasing count. I was off by 5 minutes, so sorry for rushing you there.
You had me when you said 5 minutes, but I didn't want to argue with you.
Sorry.
No, it's okay. I got through it. So are there any questions that I can raise, or and Antonio, if you're online, if you want to hop on. Antonio did all the implementation for tuxmake, and he did a really nice job.
I think for us, we're looking to leverage the build capacity is really our CI right now. We're kind of using a free tier of Travis, and I think even the paid tiers just kind of let you expand a little bit the number of concurrent jobs you have. They don't necessarily speed up the overall build itself. So I think for us, our CI does like kind of build tests and boot tests, and the boot tests don't do a whole lot of testing in user space right now, and they're relatively cheap and quick. It's more so build time is where we're tied up. But we've been getting a lot of questions lately of like, can we get access to a individual contributors, right, to our project have been asking, like, is there any service that we can have access to that are beefier build machines? And I think it might be interesting to discuss, could we get corporate sponsorship from some of the entities interested here to help our contributors actually leverage this? I think would be interesting for us to follow up on.
There are a few questions in the chat. So, how much of the 15-minute build is actually compiling time? And is there any hope of speeding up with additional resource users?
That's the end-to-end time. And so there is overhead to get your Git source and stuff like that. I would say not a lot of, I guess I don't know how much of that example was compile time. When it's well cached, a lot of the time is spent downloading artifacts from the distributed cache and stuff like that. But we try to eliminate as much of that overhead as we can to make it fast to get to the build part.
Okay. So the container already contains all the tool chains, all the known Git objects and all that? Do you have to install anything inside of the container before it actually starts compiling?
No, I mean, we make everything as hot as we can. So there's no runtime installation of anything. We even put the Docker containers on the system to start with so that we don't have to download them and things like that. It uses a distributed cache. So this is a very cloud scale sort of ephemeral share nothing architecture. So we don't have a persistent system. Everything is done at runtime very ephemerally and very quick. Yes, Jeff.
Can you speak at all to sort of plans and thoughts around running either performance tests, regression tests, self-tests, stuff like that, which usually is the sort of like boot testing after you've got a build?
So with regard to Kbuild, you could imagine a service that's similar that does something like booting or validating kernels for sure. With regard to TuxMake is scoped strictly to build. So, but we would like to support targets like kself-test and other in-tree targets, perf, CPU power, things that people should build and maybe don't always. Even documentation, it should be able to build documentation.
Okay, thanks.
Mm-hmm.
Another question in the chat. Do you post your Tux build reports, for example, to Linux stable melodies for stable releases?
So LKFT is a public project, and so its Tux builds are public, but they're not aggregated in a way that you could browse them. You can go and look at LKFT's GitLab to see the Tux builds. They often do get posted to mailing list as a part of reporting build problems. But no, there's not like an aggregated thing that shows all of the Tux builds that have happened.
Another question, do you support distributed compiling? I guess this is yeah, go ahead.
Yeah, so we made the decision to build the kernel like a Linux kernel developer would build it. And distributed compilation brings in its own caveats and constraints. And so, no, we try to build like a normal user would build, not like, with the exception of using things like Ccache.
That's on the Tux build side. So on the TuxMake side, we do support compiler wrappers. So right now we support Ccache and sccache. So we could also have support for gistcc. So you can do a distributed build on your side if you want. We have 1 minute left. You mentioned a Python library for TuxMake. What functionality does it expose? So right now the Python library exposes just one function, which is build this kernel with these parameters. So, so that's pretty much what we have now. We have some introspection to list supported architectures and targets and toolchains, but the main point is actually doing the build.
Yep, and distro Clang versions was the question, Antonio. Do you want to take that quick?
Yes. So if you are building on your host, then it is going to use whatever you have installed. If you choose the Docker runtime, then it's going to use the containers we prepared. So we have, usually we have Clang from Debian, but we can also build a container that takes Clang from AppStream or nightly build or whatever.
Cool. All right, thanks, guys. I'm going to get started on the on talking about CI systems with Clang. So pretty much just 2 slides real quick. I think so. There's a lot of different a lot of different CI systems in place for the kernel, and a lot of them we've been working with folks over the past year to get Clang builds wired up. And I think one of the things, kind of some of the ideas I have on, I'd like to try to get on the emoji. Sorry, I can't spell. Oh well. Some of the ideas I'd like to get on the radar here is, this is kind of our only status update. These architectures are supported by both Clang, LLVM and the kernel, relatively well tested kind of thing. PowerPC and MIPS builds, caveats here, there's plenty of configs that are broken still that we're still working on fixing. But for PowerPC and MIPS, these we have wired up in our testing. And then I would say out of the broken list, RISC-V is one that we get it working and then it regresses pretty quickly. S390, we're having some issues around kind of boot testing, but we are doing builds with it. Hexagon, the last time I tested it was one bug off. I don't know if there's more stuff broken. And then I think Spark was pretty busted when Arn tested that, and Arc, I don't know anyone who's tested that. But I think it would be interesting for the folks maintaining CI systems to, keep an eye on this list. At least, these architectures will be kind of future requests from me. Maybe this is one to keep an eye on. We'll see. But it would be interesting for us, at least for kind of build tests, to keep an eye on these architectures. And it would be great to implement, I think, LLVM backends for these kind of thing. But I think I'll refer people to Arn's presentation on architecture plans. It's always a trade-off in time. Is we only have finite resources to fix a lot of these things, and do we spend the resources we have fixing bugs here in these architectures, or do we spend the time implementing architectures for which kernel developers are considering removing as a backend kind of thing? So, kind of trade-offs there. But in a perfect world, we would have LLVM backends, at least to match GCC and be competitive there. And then I guess the only other thing that I'd like to bring to attention is, so when we talk about building the kernel with Clang, the Kbuild system makes it easy to kind of swap out compilers, right? The implicit default is GCC, and then you can explicitly specify, any other compiler, right? Is how you do build with Clang today. But as part of building out a compiler and a test suite for a compiler, we found you kind of need to have almost all substitutes for binutils. And by having a lot of these different parts of classes that represent ELF objects, right? It makes it much more straightforward to implement a lot of these actually. So LLVM has, it has its own linker, it has its own archiver, different binaries that you might find in binutils for dealing with kind of ELF objects. And the idea is we really would like help getting coverage of these and testing these. So not just ensuring that we can build the kernel with Clang, but really, can we ensure that no changes on the LLVM side break any of these LLVM utilities, at least for the purposes of the kernel, and to actually try to help us find, missing compatibility there. So one of the things that we did in the 5.7 release is this LLVM equals 1 patch, and that allows you to kind of flip all of these on by default, right? So, if you were going to try to specify all these at the command line, it kind of sucks. It's really verbose, and that feedback was loud and clear. So, we added it to the documentation, but I'll need some help with folks on the CI side to help us test this LLVM equals 1. And, I think given unlimited resources, it might be interested to kind of mix and match some of these, instead of doing compiles with Clang, can we ensure that CC equals GCC works with LLD, right? Because right now that's probably going to be your fastest option if you want to actually do a build and you're concerned about build times, right? And I think for a first step, we're more interested in ensuring that all of the LLVM side of things work correctly together. And then, from there, I would consider it a long tail of, this combinatorial explosion of how do we ensure all these different things work. And I think, it gets a lot more complicated when you specify and mix and match all of these kind of thing. But the idea of like, could we expand a rand config to kind of randomize these inputs might be interesting, kind of thing, certainly from a compatibility standpoint. So that's pretty much all that I had that I wanted to communicate with all of the kind of CI folks, hopefully together in one room. So pretty much nothing else I had planned. I'll just open the floor if people want to have general discussions about CI or Clang or anything like that. So open floor. So Ken asks, do we use the internal assembler? So we do not yet. So I think this is one of the things is, we feel pretty confident about a lot of these. There's some big missing pieces out of LLD, like big endian support right now is kind of tough for us, is missing. Should be using a red pen here maybe, but it's actually a separate option that we have to specify LLVM, and we call it IAS, is the integrated assembler. You actually invoke Clang as the driver. There's a utility called LLVM AS, and it's actually the assembler for LLVM IR. Doesn't assemble assembly code. So this is a flag that we kept separate from LLVM equals 1 because we were much more confident with these and less so with setting AS equals Clang. So this used to be the syntax, is you could say AS equals Clang. And we actually got rid of this. So this doesn't work anymore. So don't try this. The new name is that. And the discussion there was basically, once we're in a state where we're more confident in Clang's assembler's compatibility with gas, then we'll just roll it into LLVM equals 1 kind of thing. And at least, so technically my employer is, like, I work for Google, but my chain of command is up through Android. So for Android S, we're going to try to push for enabling Clang's integrated assembler for Android S or 12, I guess. I don't know anymore, but I think we're kind of hedging our bets there in case anything regresses that we can turn it off quickly, kind of thing.
So could this be done based on configuration? So we use LLD and the integrated assembler if we're building some configuration with some compiler version, but not in some other configuration?
Yeah, I think it's interesting to try to make these config options. The only thing that makes me nervous is around some of the shell scripts that try to bisect or add configs. I just get nervous if they may accidentally drop like one of these settings or have some issue. But we could always fix those tools, right? It's certainly probably not impossible. But I think if I understand your point correctly, you're saying like maybe it would be interesting to have a menu config to let you like maybe so this fits in a little bit with what
the question was whether we could make it so that, for example, on 32-bit ARM we don't use LLD, and on 64-bit ARM we use LLD for little endian but not for big endian. But it's not a configuration symbol. It's just that the effect of passing LLVM equals 1 depends on the configuration that is being used at that point.
Yeah, so like you're talking about not letting us, like for example, on like 32-bit ARM, we can't select like CPU big endian if LD equals LLD or LD equals LD.LLD is passed to make. Am I understanding that right?
That would also work. That would be the opposite of what I suggested. Okay. But yes. That could also clearly work, that we add the kconfig dependencies based on the command line. I was thinking we change the effect of the command line argument based on the configuration. So that
I think one thing that can be tricky is for triaging or diagnosing a build failure. If you have a log that says you invoked make LLVM equals 1, but you don't necessarily have the configuration, it may be hard at a future date to to work backwards and figure out which tools precisely were used in the build, kind of thing. And even myself, for checking build hermeticity, which is something that we're working on for Android as well, essentially being able to build kernels out of Docker images and ensure there's no hard-coded dependencies anywhere. Sorry, I lost my train of thought there, but
is it worth listing the tools that are used at the beginning of the build?
Yeah, so sorry, that's what I was going with. So for instance, our CI will set like +X to see exactly what we set in the environment, kind of thing, or set -X, I think, in the shell script. And another thing that I do a lot actually for kernel builds is like I'll rerun a make invocation with capital V = 1 make parameter to like verify that exactly this binary was executed or exactly these flags were set, kind of thing. And having that visibility on a build is really helpful to people that need to go in and triage failures from various CI reporting stuff.
It'd be really nice to have that just generally at the beginning of all builds, though, regardless of whether it's GCC or what have you, the version of GCC, LD, and so on and so forth. Bin utils, I suppose, strictly.
So some questions from chat. So Mesahiro asks about having config LD is LLD. So did we add that? I think that's in there now, right? Am I forgetting? Yeah, okay. Yeah, so we have that. I guess the hard part is you want to extend this to every single utility in this list here. What would it and what might it bias is tricky. I don't know yet. But another question is, if I set LLVM 1, can I still overwrite LLD or would LLVM overrule the other tool related variables? So right now it's set up as like an if-else statement. So if you say LLVM = 1, then you're getting all of these, and you can't then disable things one at a time. So it would make things nice, I think, to be symmetric. But I think we went with keep it simple in the kconfig. And if people really care about precisely mixing and matching, then they have very fine-grained control. And yeah, it's going to be a little painful. But this is the whole design idea around LLVM = 1 is to make it simpler for people who do want to opt into all of these things, kind of thing. And then if you really care about mixing and matching, then yeah, you're going to need the verbose kind of input, kind of thing. But it's probably not too bad or too icky, I don't know, to fix in the make file.
Just for the record, it does actually work. You can write like LD equals LD, LLVM = 1, and you'll build with LD. And I know that because it works for RISC-V. Like we need GNU LD because LLD doesn't support the relaxation options, but LLVM = 1 makes everything work. So.
Sorry, yeah, I stand corrected. Arn mentions make-s. So
this was a reply to Bian's question about always printing the build environment when doing make. And I basically said, well, we don't want make to have any output, ideally, if everything goes right in the typical build, automated build setup. If you do a manual build, you might want to pass -s. But if you don't want to pass -s and get tons of output, then it probably makes also sense to print those. Or you might have another build target, so make build environment something, and that prints all the data, like make help does. And that could also be added to automated builds.
One question I have for CI implementers is, what can we do on the kernel side, or maybe even the tool chain side, that would simplify some of this, or whatever was on the previous slide.
So one thing that I've actually always wanted was a script that just picks a tool chain and sets all the parameters based on the architecture that I'm building for, so I don't always have to type all the arguments. And I've started writing a script, but I couldn't finish it. If anybody wants to take over, I can send you my draft.
I think one thing I would like to investigate, so I find right now with Kbuild that, feedback we had was like, wow, using LLVM is kind of verbose, right? And so that was kind of the genesis for this LLVM equals 1. But I see that same problem myself when cross-compiling. So one of the things I find a little frustrating when cross-compiling is having to specify the environment variable cross-compile, right? So
worse than that, if you've got more than one cross-compiler installed, which one's being used?
Right. So, but I feel like this is very flexible. It's used as a prefix for finding the tools, and then we piggyback off this when building with Clang to set the target triple. But I feel like when I say arch equals ARM64, I feel like we could probably rely on conventions over configurations to not have to specify this. I'm pretty sure the prefix for the exact bin utils I want to use is pretty standard across multiple distributions. Like maybe if cross-compile,
it really isn't, because depending on how you build your cross-compiler, it's going to be massively different. I have ARM probably has more, but I think I have 6 different ARM compilers installed.
But we could enumerate them. We could, like, I've tried to come up with a pattern match for the shell script, so we can find all the ones that we have seen in the past, like for different versions, different installation trees, different target triplets based on the architecture. And then
I feel like we could have logic that says if cross-compile was not set, default to a convention, right? Like this is flexible if you want to name your bin utils whatever crazy naming convention you have. And unfortunately, we have to do this for Android kernels because they've made up their own convention for like the binary name, right? But
problem is the vendor, though. Is if the vendor is set, then it could be anything. That's the problem. The vendor and the triplet.
But I mean, I think Nick's suggestion there, you can we try and have a default, and then you can use cross-compile to override it. I think that makes sense because he's right. That will work a lot of the time, and it just becomes a bit inconvenient if you want to use a toolchain that's buried in some random directory because it was you just built tip of tree version of a compiler to test the bug fix out or something like that.
But in that case,
I think default's a great idea. I'm okay with that.
I would say in the case, because we get this question a lot, because I think Debian will suffix the Clang binaries with a version number. And really my recommendation for people there is, that's what the path environmental variable for is if you want to limit yourself to certain tools, like we want to ensure the build is hermetic, really like utilize your path to lop off access to these different binaries if possible, kind of thing. I think the tricky part is I want to have all my bin utils in the same directory, but they're different versions, and you're like, so path's not going to work for that, right?
Alternatives solves, to choose your default.
Although, the alternatives get annoying when you are trying to do, like I'm routinely trying to go between different compiler versions to work out whether my new compiler, my new feature will work with all the different compilers and things like that.
The minimum, I guess, should be to just print an error message when we're building for an architecture that does not match the architecture of the compiler that we are passing.
Great idea.
And then we can print the names of the compilers that are. I was going to say, then we can just print the possible options for compilers that the kernel has found to be installed, if any.
So Guillaume mentions that merge config, LLVM 1 works with merge config, but it's going to try to invoke LLD, and it seems like LLD is not overridable. I think we've run into a couple issues where, like one of the curious things, if you know a lot about variables in GNU Make, is they have a notion of an origin, and that like you can differentiate between, was a argument or a variable like set by an environment variable that invoked make, or was it set in the command line? And one of the things that gets really tricky, at least when I was looking into this, was that the recursive make invocation that Kbuild uses, there's one case where it becomes ambiguous between, was this variable set in the environment versus when make reinvoked itself. You know, I think the origin there's an ambiguity that you can't differentiate with, kind of thing. But Guillaume, do you want to expand on some of these issues you've been running into?
Yeah, so the root cause of that is because like you've explained, between environment variables and things you pass after make on the command line, because merge config.sh calls make inside, and if it doesn't forward some of the environment variable stuff to make, then that doesn't work. Now with Llvm equals 1, that works, but in kernel CI right now we're building with Clang as a compiler and the GNU linker, and I guess we could switch to use the Llvm linker as well, and that would work. That would already be some progress, because right now there are some configs we can't build with Llvm, like big endian, for example. We dynamically have a fragment to switch big endian and other things like that, like debug configs and stuff. So at least we would be able to build that. But I think for coverage, it would be useful to be able to do both linkers, to have Clang with the GNU linker and Clang with the Llvm linker. And it looks like there's still no way of doing that with the merge config.sh. So we've been tempted to have our own way of creating a config file, and I think that's what Android is doing. I think when we discussed that before. But the thing is, it's actually, the issue is not just for merge config, it's also for other things as well. When you whenever, I think I've seen it in a couple of other cases, because not all the environment is propagated when you have a submake being called, then it happens in other places. So it would be really good to have that fixed in the kernel tree, so it doesn't keep coming back all the time. I submitted a patch a while ago, like a year ago, in the top level make file. If you replace the equal signs with $equal for CC and all that stuff, then it will take whatever is in the environment instead. But people thought that maybe it would break some existing use cases where people relied on the current behavior of it. So I think that's not a solution. That's, if you want to do that locally, it's an easier way out. But we don't want to carry a patch like that in kernel CI, and I don't know what other people want to do with it.
It might be worthwhile to dust it off and resend it, and then just below the fold put like the link to the previous lore thread. I personally I forget the details of what was discussed on that thread, kind of thing. But it probably would make people's lives a lot easier if we could specify all these things from the command line.
Yeah,
but honestly, I forget the details.
I see Masahiro-san is on the chat, and I think he's, yeah. And so he said that was not a good way to do it at the time. Maybe he has some comments right now. Maybe he forgot about that. But yeah, it's probably a good idea to revive it. Now we have Llvm, like reconsider everything and see whether we can do something about it now. Thanks.
Yeah, so I'm just going to note that I'll be hanging out in one of the hack rooms afterwards, if people are interested in still just general chat about whatever kind of thing. But I'm curious. I think one of the things that we need to do on the LLVM side, so I'm impressed with all these different services on the kernel side, right? 0-day bot, kernel CI, tux build, tux boot, tux build, tux make. And we're running some CI just on Travis. Actually, it was funny. I found at least 2 folks have forked it and are using it for other kernel testing, which I thought was funny. Cool to see that. And then some Linaro toolchain folks actually have their own really cool service that does automated bisection, which was really nice. I don't know if any of them are here today. I think there may have been issues getting tickets. But I think they have a really cool service. And I think one of the things that we need help with is on the LLVM side, there's not a lot, like there's in-tree pre-submit tests, but they still are heavily dependent on your host. And one of my experience contributing to LLVM is I feel like I constantly break the Windows build. And you kind of find out in post-submit. There's a lot of post-submit coverage, but we probably need to figure out how to stand up a LLVM side build bot. So one of the things that the LLVM meetup that's going to be later this year, I'm going to talk about in the BOF is, I don't know, how do we stand up a Linux kernel build bot so that LLVM developers get warned when they break kernel builds unintentionally.
Sure, yeah. Yeah.
As a heads up, being your microphone's on.
Imported into Final Cut and then export.
Any pie in the sky ideas for what we can be doing for testing?
It reminds me a lot of Rust's Crater in the sense of the Rust team, I think manually and possibly before release, but certainly not on every commit, has the ability to say, I want to run Rust compiler on all the Rust code I know of. And I think in addition, I want to run it on some particular build workers at private companies on their internal code bases, and I don't get any information. I just get like a yes, no, follow up with them if you want to see what's wrong. And so when they're planning on deprecating some wacky syntax that they think no one has ever run into, they want to make sure of that. They have the ability to do that. I don't know if Crater itself as like an actual implementation tool is the thing you want to use. I assume it is not, but chatting with some of the folks behind it as to how has this worked out for you sounds probably like what you want.
Yeah, I mean, we have some stuff like that internally, but I think the thing here is getting something like the service that was just described, where we can contribute, or the different people can contribute information back, rather than having to do it. Everybody having to do the infrastructure or do the reporting side of it themselves. Having it all go to a central place where it'll get paid attention to, hopefully.
Kevin asks, does LLVM equals 1 work with Ccache? So no, it doesn't, because it hard codes Clang as the CC invocation. So I guess you might have to do LLVM equals 1 CC equals quotations Ccache Clang. So that's how you set Ccache's fallback kind of thing. Nathan Chancellor says that should work. Cool. Right, we got a minute left. So, oh, sorry. Go ahead, Case.
Oh, I was just going to say, shouldn't we be able to fix that? I mean, it seems like a pretty distinct problem with Ccache, but anyway, not useful for me to mention. So I'm sorry.
No, it's all good. Cool. All right. Thanks everyone for attending our micro conference. I hope there was something interesting here for you. This has been a multiple person project for over 10 years, and it's really something I enjoy being a part of, and I've learned an awful lot about kernel development and toolchain development from working with all of you. It's something I've been very, very proud to work on. So, thank you all for joining us today and this week. I'm gonna go hang out in one of the hack rooms if you wanna, shoot the shit about whatever. So, thanks for joining us, and see you next year, I guess.